Hello there and welcome to Science for Sleep, where curiosity gets comfortable, complicated ideas are given plenty of room to breathe, and the universe is allowed to be enormous without anyone demanding that we understand all of it before bedtime. Tonight, we're going to explore the structures that make up the universe. And when I say structures, I don't just mean planets, stars and galaxies. Those are certainly part of the story, but they are only the beginning. The universe organizes matter on a remarkable range of scales. There are planetary systems gathered around individual stars. There are clusters containing hundreds of thousands, sometimes millions of stars. There are enormous clouds of gas and dust where new stars are being assembled. Galaxies themselves gather into groups. Groups collect into clusters. Clusters form parts of even larger arrangements. And eventually, when we zoom out far enough, we reach filaments, walls, voids, and the immense pattern known as the cosmic web. It is a little like discovering that your house is part of a street. The street is part of a town. The town sits inside a region, and the region turns out to be one small thread in a network stretching farther than you can reasonably picture. Except in this case, the house may contain a few 100 billion stars. So perhaps check the loft before moving in. Before we begin working our way through all of these structures, I'd love to know where you're listening from tonight. What part of Earth are you in? Maybe you're somewhere where the sky's already dark and a few stars are visible through the window. Maybe you're listening in a city where the night sky has been mostly replaced by streetlights, glowing windows, and one neighbour who appears to believe their garden needs airport runway lighting. Or perhaps it's daytime where you are, and you're simply here because listening to someone calmly explain galaxy clusters is a perfectly reasonable way to spend an afternoon. Wherever you happen to be, you're already inside the first important fact of tonight's journey. You're not looking at the universe from the outside. You're inside one of its structures. Right now, you're standing or lying on a rocky planet called Earth. Earth belongs to a planetary system centered on a star, the Sun. The Sun belongs to a galaxy called the Milky Way. The Milky Way is part of a small collection of galaxies known as the Local Group. The Local Group sits within a much larger region of galaxies, and that region connects into the enormous network of matter that extends across the observable universe. So when astronomers study cosmic structure, they are not examining some distant arrangement that has nothing to do with us. We are part of the arrangement. We're sitting inside it. Admittedly, from our point of view, it doesn't always feel especially organized. Your desk might disagree with the general idea of cosmic structure entirely, but on large enough scales, the universe has a surprisingly clear hierarchy. Matter gathers, gravity pulls, gas collapses, stars form. Stars gather into galaxies. Galaxies gather into groups and clusters. Then those galaxies and clusters trace huge filaments, separated by vast regions containing much less matter. The result is not a universe in which everything is spread evenly like sugar stirred perfectly into a cup of tea. Matter is clumped. Some places are crowded, others are almost empty, and that unevenness is one of the most important features of the cosmos. If the universe were perfectly smooth, there would be no galaxies. There would be no stars, there would be no planets, there would certainly be no one lying in bed listening to a suspiciously relaxed explanation of large-scale cosmology. The fact that anything exists in recognizable structures is connected to tiny irregularities that were present very early in cosmic history. Shortly after the beginning of the universe, matter was distributed almost evenly, but not completely evenly. Some regions were slightly denser than others. We're talking about very small differences, the sort of differences that would look unimpressive if you were hoping for dramatic cosmic architecture. But gravity is patient. Give gravity a slightly denser region and enough time, and it begins pulling more material toward that region. More matter increases the gravitational attraction. That attracts still more matter. Over hundreds of millions and then billions of years, those tiny early differences grew into larger concentrations. Dark matter played a central role in this process. Unlike ordinary matter, dark matter does not emit light, reflect light, or absorb light in the ordinary way, which is rather inconvenient for something that appears to make up most of the matter in the universe. We cannot simply point a telescope at a lump of dark matter and say, "There it is." Instead, astronomers infer its presence through gravity. Dark matter helped form the underlying gravitational framework into which ordinary matter could fall. Gas collected in these regions, stars formed from that gas, galaxies grew, galaxies merged, larger systems developed. If you could somehow remove all the stars and glowing gas from the universe, but leave dark matter behind, much of the large-scale structure would still be there gravitationally, though it would be completely invisible, which would make astronomy considerably more difficult and less decorative. The structures we'll explore are therefore not simply objects floating randomly through empty space. They are the result of cosmic history. Each one tells us something about how matter behaves under gravity, how stars are born, how galaxies evolve, and how the universe changed from an almost uniform early state into the complicated place we see today. Some of these structures are easy to imagine. A planetary system, for example, is relatively familiar. We live in one. There is a central star, planets orbiting it, smaller objects scattered around, and perhaps a few icy bodies spending most of their existence very far away, quietly minding their own business. Star clusters are already more impressive. Thousands or even millions of stars can occupy the same general region, bound together by gravity. Nebulae can stretch across dozens or hundreds of light years, containing enough gas to produce generations of stars. Then we reach galaxies. Galaxies are among the great organized systems of the universe. Some contain only millions of stars. Larger ones contain hundreds of billions, and some especially massive galaxies contain even more. They also contain gas, dust, stellar remnants, planets, black holes, and enormous amounts of dark matter. Our own Milky Way is just one. That fact is easy to say. It is harder to absorb. For most of human history, people looking at the pale band of the Milky Way across the night sky had no way of knowing that it was a view from inside an enormous galaxy. They certainly had no way of knowing that beyond it were hundreds of billions of other galaxies across the observable universe. Once you start thinking at that scale, the word large stops being very useful. It becomes a little like describing the Pacific Ocean as damp. Technically correct, not especially informative, and galaxies themselves are not evenly scattered. The Milky Way has companions. The largest nearby major galaxy is Andromeda, and together with the Milky Way, the Triangulum galaxy, and many smaller dwarf galaxies, it forms the local group. Even that is not isolated. Galaxy groups exist alongside galaxy clusters, which may contain hundreds or thousands of galaxies packed into a region bound together by gravity. Between those galaxies is not simply empty space. There can be extremely hot gas, magnetic fields, high-energy particles, and enormous quantities of dark matter. At the centres of many large clusters sits an enormous galaxy, often surrounded by other galaxies moving through the cluster under the influence of a gravitational field produced mostly by matter we cannot directly see. Then things become less tidy. When astronomers zoom out farther, galaxy clusters and groups are found arranged along larger patterns. There are superclusters, although the word can be slightly misleading because these enormous regions are not always gravitationally bound together as one single object. Beyond that scale, the universe begins to resemble a network. Galaxies trace long filaments. Clusters appear where filaments intersect. Broad sheets and walls of galaxies stretch across astonishing distances. Between them lie cosmic voids, huge regions containing far fewer galaxies than average. This network is the cosmic web. It is one of the largest patterns we can observe. If you have ever seen a computer simulation of the large-scale universe, it can look almost biological. Bright strands connect thicker knots, while dark spaces open between them. But there is nothing biological about the mechanism producing it. Gravity, dark matter, expansion, gas physics and billions of years are quite sufficient. The resemblance is just something our pattern-loving brains notice. Human beings are extremely good at finding familiar shapes in unfamiliar things. We see faces in clouds, animals in constellations, and occasionally a meaningful life philosophy in the pattern left by spilled coffee. So a giant simulated section of the universe resembling a network of neurons can feel strangely significant. It is interesting, it is visually striking. But the universe is not literally a giant brain. Your brain may be relieved to hear that it does not have that much competition. What is particularly useful about studying cosmic structure is that size changes the kind of physics we notice. At small astronomical scales, individual objects matter. A planet orbits because of the gravity of a star. Two stars in a binary system orbit each other. A star cluster remains together because its members are gravitationally interacting. Move outward to the scale of a galaxy, and millions or billions of objects contribute to the system. Move to galaxy clusters, and dark matter becomes impossible to ignore. Move to the larger scales, and we begin thinking about the expansion of the universe, the initial distribution of matter, and the overall evolution of cosmic structure. The same universe looks different depending on how far out you zoom. Imagine opening a map. At first you see individual streets. Zoom out and the streets disappear, replaced by towns. Zoom out again, and towns become small marks inside counties or regions. Eventually whole countries become shapes. Keep going and the planet itself becomes a sphere. Nothing actually vanished when you zoomed out. The information simply changed. Astronomy works in much the same way. A single star can be an object of intense study. Astronomers can examine its temperature, mass, age, chemical composition, rotation, magnetic activity, and planets. But if you're studying the structure of the Milky Way, that same star may become one data point among billions. If you're studying the local group, the entire Milky Way becomes one object. If you're mapping the cosmic web, even the local group barely registers. Scale changes perspective rather dramatically. It also changes what we mean by a structure. Some cosmic structures have obvious boundaries. A star has a surface, even if it is not a solid surface like the ground beneath your feet. A planet is fairly easy to locate. Other structures are much less definite. Where exactly does a galaxy end? There are stars far beyond the bright visible disk of the Milky Way. There is a vast halo of dark matter extending much farther still. Where does one galaxy's gravitational influence stop and another begin? Where does a supercluster end? At large scales, astronomers often have to define structures using density, motion, gravity, or statistical patterns rather than neat physical edges. The cosmos has not provided labels. There is no sign floating outside the local group saying, "You're now leaving, please drive carefully." The categories are human tools. They help us describe patterns that genuinely exist, but nature does not always separate those patterns into perfectly convenient boxes. That makes the subject more interesting rather than less. We will encounter structures that are tightly bound together by gravity, and others that are simply part of a larger pattern. We will meet objects created by collapsing gas, systems formed through repeated mergers, and enormous regions defined partly by what they do not contain. Voids, for example, deserve more attention than the word void might suggest. A cosmic void is not necessarily completely empty. It simply contains much less matter than denser regions around it. There can still be galaxies inside, just fewer of them. Calling a cosmic void empty is a bit like arriving at a restaurant with 2 people inside instead of 200, and declaring that civilization has vanished. Quiet, yes. Completely empty, no. And that difference matters because voids help astronomers understand how matter has moved through cosmic history. Dense regions attracted material. Less dense regions lost material relative to their surroundings. Over time, the contrast became stronger. The universe developed texture. That texture is what we're going to follow. We'll begin close to the scale that feels most familiar, with stars and the systems that form around them. Then we'll move outward, slowly. There is no need to jump immediately from Earth to a billion light-year filament. The universe will still be large when we get there. We'll look at how stars can exist alone or in groups, why star clusters come in different forms, and how great clouds of gas act as raw material for stellar formation. We'll move into galaxies and see that they are not simply collections of stars but evolving systems with complicated histories. We'll examine the smaller communities galaxies form, followed by the enormous galaxy clusters that rank among the largest gravitationally bound structures known. From there, the boundaries become broader. Superclusters lead us toward filaments, walls, and voids. Eventually, all of those pieces reveal the cosmic web, the large-scale arrangement that emerged from conditions established near the beginning of the universe. Along the way, there will be some very large numbers. Astronomy is fond of those. Distances in kilometers quickly become inconvenient, so astronomers use light years and parsecs. Masses become so enormous that using kilograms can feel like trying to count a forest by weighing every leaf. We will keep the numbers useful rather than letting them turn into a bedtime mathematics examination. The goal is not to memorize measurements. It is to understand the hierarchy. Where are we? What surrounds us? What surrounds that? And how far does this nesting of structures continue? There is something reassuring about knowing our cosmic address. Not because it makes the universe smaller, it does quite the opposite. But it gives the scale some organization. Earth is not simply somewhere in space. It has an address. Earth, solar system, Milky Way, local group, larger scale regions beyond that, cosmic web, observable universe. You can keep adding levels depending on exactly how astronomers define the structures involved. It is the most excessive postal address imaginable, and delivery remains unreliable. If you find this kind of slow tour through science soothing, intriguing, or simply useful, when your brain has decided that bedtime is the perfect moment to reconsider the scale of existence, you can give the video a like and subscribe to Science for Sleep. It helps other curious night owls find this quiet part of the internet, and it lets us continue taking complicated subjects apart without shouting about them, adding dramatic countdown clocks, or insisting that every astronomical fact must be the most shocking discovery in human history. Sometimes the universe is impressive enough without assistance, and tonight's subject certainly qualifies. Think for a moment about the room around you. Maybe there is a lamp nearby, a window, a phone resting beside you, perhaps a cup of tea that was supposed to be finished 20 minutes ago. Everything you can touch is made of matter that has been through a very long sequence of cosmic structures. The heavier elements in your body were produced inside earlier generations of stars or during violent stellar events. The material that eventually became the solar system gathered inside a cloud of gas and dust. That cloud collapsed. The sun formed. A disk of material developed around it. Planets grew from that disk. One of those planets became Earth, and much later, a small portion of Earth's material became you. So cosmic structure is not only about where objects are arranged today, it is also about how matter moves from one structure into another. Gas enters galaxies. Galaxies form stars. Stars manufacture new elements. Stars return material to space. New stars and planets form from enriched gas. Galaxies collide. Clusters grow. Filaments feed dense regions. Nothing about this arrangement has been static. The universe has been building, merging, separating, collapsing, and expanding for billions of years. Even now, our own galaxy is changing. Stars are being born. Other stars are dying. Small galaxies are interacting with the Milky Way. Andromeda is approaching. The local group continues moving within a larger gravitational environment. On scales far beyond our galaxy, the expansion of the universe continues. There is movement at every level. Not always movement we can notice during a human lifetime, of course. Astronomy requires a certain tolerance for slow events. a galaxy merger can take hundreds of millions of years, which makes waiting for a software update seem reasonably efficient. But because light takes time to travel, telescopes let us observe different stages of cosmic history. Looking far away also means looking into the past. A galaxy seen billions of light years away is seen as it was billions of years ago. By examining large populations of distant objects, astronomers can reconstruct how structure developed across time. They do not have to wait around for a modern galaxy to become ancient. The universe has already provided examples at different distances. Light carries the evidence toward us. That is one of the reasons the night sky is much more than scenery. It is a record. Different objects show us different periods. Different scales reveal different physical processes, and together they allow us to assemble a picture of how the organized universe developed. The picture is still incomplete. Dark matter remains mysterious. Dark energy remains even more mysterious. Astronomers continue debating details of galaxy formation, feedback from stars and black holes, the growth of early structure, and exactly how some of the first large systems appeared as quickly as they did. Science has not finished the map. It rarely does. But the overall structure is clear enough for us to travel through it. We know that matter forms a hierarchy. We know that gravity shaped small early density differences into much larger structures. We know that dark matter supplied much of the gravitational framework. We know galaxies gather into larger systems, and we know those systems trace an enormous network extending across the observable cosmos. Our route, then, begins at the smaller end of that hierarchy. Not with Earth itself, because Earth is only one member of a much larger family, but with the kind of object that organises our immediate astronomical neighbourhood. A star. The sun looks singular from here, one bright object crossing the sky every day. But stars rarely tell their whole story when viewed alone. Some have planets, some have companion stars, some are born inside crowded clusters, some remain surrounded by debris left from their formation. Some end their lives and alter the environments around them, supplying material that will later become new stars, new planets, and perhaps new places where someone eventually lies awake, listening to an explanation of cosmic structure. Our own sun sits at the centre of a system that extends much farther than the orbit of Neptune. 8 major planets travel around it, along with dwarf planets, moons, asteroids, comets, dust, and small bodies in several distinct populations. Far beyond the familiar planets lies material left over from the solar system's formation. Even farther out, the sun's gravitational influence continues into a region where the boundaries become difficult to define neatly. And the solar system itself is moving. The sun travels around the centre of the Milky Way, carrying Earth and the rest of its system along with it. So our first step outward is already a moving structure inside another moving structure. That is where the hierarchy becomes useful, and the most natural place to begin is with the stars themselves. The stars themselves are a sensible place to start, because almost every bright point you can see in a clear night sky is another sun. That sounds obvious when stated plainly, but it is one of those facts that becomes stranger the longer you think about it. The small white point above a rooftop may be an enormous sphere of plasma hundreds of thousands or even millions of kilometers across. It may be hotter than the sun, cooler than the sun, younger, older, larger, smaller, or surrounded by planets of its own. Some stars travel through the galaxy alone. Others live with one or more stellar companions. Many carry entire planetary systems around with them as they orbit the centre of their galaxy. From Earth, all of this complexity is compressed into tiny dots. Astronomy has spent centuries unpacking those dots. Our Sun is the example we know best. It is a fairly ordinary star by galactic standards, which is perhaps a little disappointing if you were hoping that our local star had won some kind of cosmic award. It is not the largest star, the hottest star, the oldest star, or the most energetic. It is a middle-aged, medium-sized star of a type astronomers classify as a G-type main sequence star. Ordinary, though, does not mean unimportant. The Sun contains more than 99% of the mass in the solar system. Everything else, Earth, Jupiter, Saturn, every moon, asteroid, comet, grain of dust and spacecraft humans have managed to throw into the darkness, shares the small amount that remains. This enormous difference in mass explains why the solar system is organised around the Sun. Gravity makes the arrangement possible. Earth is not held in place by a physical connection. There is no invisible cable running from the planet to the Sun, which is fortunate because someone would eventually trip over it. Earth is constantly falling toward the Sun under gravity, but it is also moving sideways fast enough that it keeps missing. That continuous miss is an orbit. The same basic idea applies to the other planets. Moons orbiting planets, asteroids travelling around the Sun, stars orbiting one another, and later, on much larger scales, stars moving around the centres of galaxies. Gravity is remarkably repetitive. It changes the size of the system, but not necessarily the basic idea. The Sun itself formed roughly 4.6 billion years ago from a collapsing region of gas and dust. As that material contracted, most of it collected in the centre and became the young Sun. The remaining material settled into a rotating disk around it. That disk was the beginning of the planetary system. Tiny particles collided, some stuck together. Those small clumps collided with other clumps. Over time, larger objects formed. Eventually, through an extremely long process involving collisions, growth, destruction, and a great deal of gravitational rearranging, planets emerged. It was less like carefully assembling furniture and more like throwing the contents of an entire warehouse into a rotating room for several million years and seeing what survived. The result around our star is the solar system we recognise today. Closest to the Sun are the 4 terrestrial planets: Mercury, Venus, Earth, and Mars. They're relatively small, rocky worlds with solid surfaces. Farther out are Jupiter and Saturn, the gas giants, followed by Uranus and Neptune, which are usually described as ice giants because their internal compositions differ substantially from those of Jupiter and Saturn. Then there are the smaller populations: asteroids, dwarf planets, comets, icy bodies beyond Neptune, dust, fragments left behind by collisions, material that never became part of a major planet. The solar system is therefore not simply the Sun plus 8 planets, arranged neatly for a school diagram. Those diagrams are useful, but they tend to make the solar system look considerably more organised and much more compact than it actually is. Real distances are enormous. If the Sun were reduced to the size of a grapefruit, Earth would be roughly the size of a grain or small seed positioned many meters away. Neptune would be far beyond that, and the distant populations associated with the solar system would extend farther still. The planets are separated mostly by space, very large quantities of it. This is something illustrations have difficulty showing, because a properly scaled diagram of the solar system would require either extremely tiny planets or an inconveniently long piece of paper, possibly both. Beyond Neptune lies the Kuiper Belt, a broad region containing many icy bodies, including dwarf planets such as Pluto. Pluto is therefore not sitting at some simple final edge of the solar system. It belongs to a larger population. That discovery was one reason astronomers eventually reconsidered Pluto's classification. As increasingly powerful telescopes revealed more objects in the outer solar system, it became clear that Pluto had plenty of company. Farther away still, astronomers think there is the Oort cloud, a vast, roughly spherical reservoir of icy objects surrounding the solar system. Unlike the planets and Kuiper Belt, which mostly occupy a flattened region related to the original disk from which the solar system formed, the Oort cloud is thought to extend in many directions around the Sun. It has not been directly imaged as a complete structure. Its existence is inferred largely from the orbits of long-period comets. which can arrive from distant regions around the solar system. The distances involved become rather inconvenient again. Depending on where one decides to place its outer boundary, the Oort cloud may extend a substantial fraction of the distance toward the nearest stars. Which raises a useful question. Where does the solar system actually end? There is no single answer because there are different ways to define the boundary. If you mean the region dominated by the solar wind, then one useful boundary is the heliopause. The Sun constantly releases a stream of charged particles called the solar wind. This material flows outward, creating a huge bubble around the solar system known as the heliosphere. Eventually, the pressure of the solar wind becomes balanced by the material between the stars. That transition marks the heliopause. NASA's Voyager 1 and Voyager 2 spacecraft have both crossed this boundary, entering interstellar space in the sense that they move beyond the heliosphere. But they have not escaped the Sun's gravity. Not even close. Gravitationally, the solar system extends much farther. The distant Oort cloud, if our models are correct, remains loosely bound to the Sun, so a spacecraft can leave one definition of the solar system while remaining inside another. Nature is occasionally unhelpful with borders. Astronomers would probably appreciate a fence. Our solar system is only one example of a planetary system, and we now know that planets are common around other stars. For a long time, this was a reasonable assumption without direct evidence. The Sun had planets. Why shouldn't other stars? But detecting planets around distant stars is difficult because planets are small, faint, and located next to objects that are enormously brighter. Imagine trying to detect a moth flying beside a lighthouse from hundreds of kilometers away. Now make the lighthouse a star and remove the moth's helpful habit of moving directly in front of your binoculars. That gives you some sense of the problem. Astronomers developed several techniques to overcome it. One of the most successful is the transit method. If a planet's orbit happens to line up correctly from our viewpoint, the planet passes in front of its star. It blocks a tiny fraction of the starlight, producing a small but measurable dip in brightness. If the dip repeats at regular intervals, astronomers can infer that an orbiting planet may be responsible. The amount of light blocked gives information about the planet's size. The timing gives information about its orbit. Another method looks for the gravitational influence of the planet on the star itself. We often say that a planet orbits a star, but more precisely, both objects orbit their common centre of mass. Because the star is much more massive, its motion may be very small. Still, sensitive instruments can detect the tiny wobble caused by an orbiting planet. The radial velocity method measures changes in the star's motion toward and away from us by examining small shifts in its spectrum. Through techniques like these, astronomers have confirmed thousands of planets beyond our solar system. These are exoplanets, and if there was ever any hope that every planetary system would resemble our own tidy diagram, exoplanets ended that hope rather quickly. We have found worlds orbiting extremely close to their stars, giant planets with years lasting only a few Earth days, rocky planets larger than Earth, planets smaller than Neptune but larger than Earth, a category that does not exist in our own solar system, planets orbiting two stars, systems packed with multiple planets in compact orbits, worlds around small red dwarf stars, planets with orbital arrangements that initially seemed very surprising. The solar system is not necessarily a universal blueprint, it is one possible outcome. That makes planetary systems useful structures to study because their architecture preserves clues about their formation. Where planets ended up can tell us something about where they formed, how they migrated, and how they interacted with disks, neighbouring planets, or companion stars. Migration is especially important. A planet does not always remain at exactly the distance from its star where it first formed. Interactions with surrounding material or other planets can shift an orbit. Some planets move inward, others can be pushed outward. Entire systems can become unstable. One world may scatter another into a distant orbit. In extreme cases, a planet can be ejected altogether. That brings us to an especially lonely member of the small-scale cosmic population, the rogue planet. A rogue planet is a planetary mass object moving through space without orbiting a star. Some may have formed in planetary systems and later been thrown out through gravitational interactions. Others might have formed in a manner more similar to very small stars. Either way, they travel through interstellar space without a local sun. There may be enormous numbers of them in the galaxy. They are difficult to detect because they do not shine like stars and may be far from any strong source of illumination. A planet drifting alone through the Milky Way is therefore one of the quieter possible cosmic neighbourhoods. Although neighbourhood may be generous when your nearest useful source of daylight is several light years away, stars themselves also come in arrangements more complicated than the Sun. Our solar system contains one star. Many stellar systems contain two. Binary stars are extremely common. In a binary system, two stars orbit a shared centre of mass. Sometimes they are widely separated. Other binaries are so close that the stars orbit each other in days or even hours. Their evolution can become deeply interconnected. A star may expand as it ages and transfer material onto its companion. The companion may be a normal star, a white dwarf, a neutron star, or even a black hole. Matter moving between stars can produce some of the most energetic events astronomers observe. There are also systems containing 3 or more stars. These arrangements can remain stable when their orbits are organised hierarchically. For example, 2 stars may orbit closely around each other, while a third star orbits much farther away around the pair. Trying to place 3 stars at similar distances in an unrestricted gravitational dance is much less cooperative. The famous 3-body problem exists for good reason. Gravity is easy to describe in a system of 2 idealized objects. Add a third, and the long-term motion can become surprisingly complicated. Yet nature manages to produce stable multiple star systems throughout the galaxy. Planets can exist in these systems as well. Some orbit one member of a binary pair. Others orbit both stars together. If you stood on such a world, depending on the system, the sky might contain 2 suns. That sounds wonderfully cinematic until you remember that orbital stability, temperature, radiation, and planetary climate are considerably more important than whether the sunset looks impressive. Between planets and stars lies another class of object worth mentioning. Brown dwarfs are objects more massive than typical giant planets, but not massive enough to sustain ordinary hydrogen fusion in their cores in the way main sequence stars do. They are sometimes casually described as failed stars, although that phrase can be slightly unfair. A brown dwarf has not personally failed at anything. It simply formed below the mass required for long-term hydrogen fusion. Some brown dwarfs can fuse deuterium for part of their lives, and the precise boundary between giant planets and brown dwarfs can involve questions of mass and formation. They occupy an interesting middle ground between planetary and stellar objects. Some have companions, some may host disks, some may even have planets. The categories we use begin to overlap. That is common in astronomy. The more objects we discover, the more nature reminds us that classification systems are tools rather than laws carved into the universe. A planet does not know that it has been classified. A brown dwarf is not checking the latest definition. And Pluto, despite several decades of public concern, appears to be coping. The star at the centre of a system has the greatest influence over its local environment. Its mass determines the strength of its gravity. Its temperature and luminosity determine how much energy reaches surrounding worlds. Its magnetic activity can affect planetary atmospheres. Its lifetime limits how long certain stable conditions might persist. A massive blue star, for example, can be many times more massive than the Sun and far more luminous. It burns through its nuclear fuel quickly and may survive for only millions of years. Smaller red dwarf stars can remain active for vastly longer periods. Some are expected to continue shining for trillions of years, far longer than the current age of the universe. This means that 2 planetary systems can have very different histories simply because their stars are different. Even the idea of a habitable zone depends strongly on the star. A habitable zone is generally the range of distances where conditions might allow liquid water to remain on the surface of a suitable planet. It is not a guarantee that a planet is habitable. Atmosphere, pressure, chemistry, magnetic environment, geological activity, and many other factors matter. Venus provides a useful warning against assuming that being approximately the right distance from a star automatically results in pleasant weather. It does not. Venus has taken a more aggressive approach. Planetary systems also contain smaller structures within structures. Earth has the Moon. Jupiter has a large family of moons. Saturn has moons, and a spectacular ring system made mainly of countless particles of ice and rock. Asteroids can have moons. Small objects can exist in binary pairs. Rings may surround planets, dwarf planets, and other bodies. At every scale, gravity keeps building little arrangements. A moon can orbit a planet while the planet orbits a star while the star orbits the galaxy. Several motions happen simultaneously. You're participating in them right now. Earth rotates. Earth orbits the Sun. The Sun moves around the Milky Way. The Milky Way itself is moving relative to nearby galaxies and within larger cosmic structures. You do not feel these motions because smooth, constant motion does not announce itself in the way acceleration does. Your bed does not slide dramatically toward the wall because Earth is orbiting the Sun, which is probably for the best. The small cosmic neighbourhood around a star also has a history shaped by things that no longer exist. The solar system once contained objects that were destroyed, absorbed, or ejected. The young planets experience major collisions. One leading explanation for the Moon's origin involves a collision between the young Earth and another large body early in solar system history. The present arrangement is therefore a surviving configuration. It is what remains after billions of years of evolution. Other planetary systems show us different outcomes. Some systems may remain calm for long periods. Others undergo gravitational instability. Stars passing relatively nearby can disturb distant comets. Companion stars can alter planetary orbits. A star evolving into a red giant can transform or destroy its inner planetary system. When the Sun eventually reaches that stage, the solar system will look very different from the one we know. Stars change, so their neighbourhoods change with them. For most of its life, a star like the Sun remains on the main sequence, converting hydrogen into helium in its core. Eventually, the available core hydrogen declines. The star expands. Later stages follow. For the Sun, the end result will be a white dwarf surrounded by material lost during its later evolution. More massive stars end much more violently, potentially exploding as supernovae and leaving neutron stars or black holes behind. Those deaths affect nearby space. They release energy. They distribute newly formed chemical elements. They can compress surrounding gas. They can alter or destroy neighbouring systems. In that sense, the boundary between one small cosmic neighbourhood and another is never perfectly isolated. Stars affect the environments around them. Their radiation heats gas. Their winds push material away. Their explosions enrich space with heavier elements. The carbon in living cells, the oxygen you breathe, the calcium in your bones, and much of the iron around you exist because earlier generations of stars produced and distributed elements into space. Our solar system formed from material that had already been processed by older stars. So even a planetary system that looks self-contained has a family history. It inherited material from the wider galaxy. The Sun did not form in complete isolation either. Stars usually form inside large clouds of cold gas and dust, and those clouds can produce many stars over time. Young stars are therefore often found near other young stars. Some remain associated loosely for a while before drifting apart. Others stay bound together by gravity. That distinction leads us toward a larger kind of structure. Before getting there, though, it helps to appreciate just how much can already fit inside what we have casually called a small cosmic neighbourhood. One star can have planets. Those planets can have moons. Moons can have complex surfaces, atmospheres, subsurface oceans, volcanoes, or icy crusts. Planets can be surrounded by rings. Asteroids can travel in broad populations. Comets can spend millions of years in the distant outer reaches before falling inward. A stellar companion may circle the system from far away. Another star might pass nearby over astronomical timescales. All of this can exist inside a region that would be almost invisible if you viewed the Milky Way from outside. Our entire solar system, enormous from the perspective of a spacecraft, is minuscule compared with the galaxy. The distance from the Sun to Neptune is measured in billions of kilometers. The distance to the nearest star is measured in light years. The diameter of the Milky Way is measured in tens of thousands of light years. Scale changes very quickly. If you shrank the Milky Way until it were the size of a large city, the solar system would be extremely difficult to notice. And yet, from our point of view, the solar system contains every place any human being has ever stood. Every city, every ocean, every mountain, every bedroom in which someone has decided that learning about the hierarchy of cosmic structure sounds preferable to sleeping immediately. That contrast between human scale and cosmic scale will keep returning. Something can be unimaginably large to us and still be tiny in the next structure up. A planet is huge compared with a person. A star is huge compared with a planet. A planetary system is huge compared with a star. The distance between stars is huge compared with a planetary system. Then even those distances begin to look small when stars gather in large numbers, and stars do gather. The Sun appears relatively isolated now, with its nearest stellar neighbours separated by several light years, but that does not mean stars always spend their lives evenly scattered through galactic space. A star cluster is what happens when the idea of a stellar neighbourhood becomes considerably more crowded. Instead of one star with a few nearby companions separated by several light years, imagine hundreds, thousands, or even millions of stars occupying the same region of space and responding to one another through gravity. Some are packed closely enough that, from a planet inside the cluster, the night sky could contain far more bright stars than anything we see from Earth. Our Sun lives in a fairly quiet part of the Milky Way. The nearest star system, Alpha Centauri, is more than 4 light-years away. Most of the stars we see at night are much farther than that. There is plenty of room between them. Inside a dense star cluster, that comfortable personal space can shrink dramatically. Stars may pass one another at distances that would seem alarmingly close by solar system standards. Their gravitational interactions slowly reshape the cluster. Binary stars encounter other stars. Massive stars sink toward crowded central regions. Smaller stars can be pushed toward the outskirts. Some eventually escape altogether. So although a cluster can look peaceful through a telescope, the stars inside it are not simply sitting in place. They are moving constantly. Each star follows an orbit through the combined gravitational field of the cluster, and the cluster itself travels through the Milky Way. Once again, everything is moving inside something else that is also moving. Astronomy rarely offers a stationary chair. The basic reason star clusters exist takes us back to the way stars form. Stars are born when sufficiently dense regions of cold gas collapse under gravity. But a giant cloud does not usually collapse neatly into a single object. It contains turbulence, uneven densities, magnetic fields, and smaller pockets of material. Different parts of the cloud can collapse at roughly the same time. One region forms a star, another forms several stars. Dense pockets continue breaking into smaller concentrations. Before long, what began as one large cloud may produce dozens, hundreds, or thousands of young stars. This means that stellar birth is often a social event. The Sun probably formed alongside many other stars. We do not know exactly which stars were its original siblings because the group dispersed long ago. After about 4.6 billion years of orbiting the Milky Way, stars born near one another can become spread across enormous distances. Some researchers have searched for possible solar siblings by comparing stellar motions and chemical compositions, but reconstructing a stellar family after billions of years is difficult. It is rather like trying to identify everyone from your first day at school After the school itself has been dismantled, the town has moved, and all the pupils have spent several billion years orbiting a galaxy. Young groups of stars do not all remain together. When stars form inside a molecular cloud, much of the original material may not become stars at all. Radiation and winds from newly formed stars begin pushing leftover gas away. Massive stars can clear material particularly quickly. If a young stellar group loses too much mass from its surrounding gas, its gravitational binding can weaken. Some stars drift apart. The group expands. Eventually the stars may become an association rather than a tightly bound cluster, and later they can disappear into the general stellar population of the galaxy. Other groups remain gravitationally bound for much longer. These are the star clusters we can observe as recognizable structures. Astronomers usually discuss two major traditional types in the Milky Way: open clusters and globular clusters. They look very different. Open clusters tend to contain tens, hundreds, or sometimes thousands of stars. They have relatively loose structures and irregular shapes. Most are found in the disk of the Milky Way, the same broad flattened region where much of the galaxy's gas and active star formation are located. Many open clusters are young. Some are only a few million years old. Others survive for hundreds of millions of years, and a smaller number remain recognizable for billions. One of the most famous examples is the Pleiades. Even without a telescope, the Pleiades can be seen as a compact little group of stars in the constellation Taurus. Depending on your eyesight and sky conditions, you may see 6 or 7 bright members, although the cluster actually contains many more stars. Through binoculars, the view changes immediately. More stars appear. The compact little patch becomes a much richer group. The Pleiades is only about 100 million years old, making it extremely young compared with the roughly 4.6 billion-year-old Sun. Some of its stars are still surrounded by or passing through dust that reflects their light. Another nearby open cluster is the Hyades. It is older than the Pleiades and more spread out across our sky because it is relatively close to us. The bright orange star Aldebaran appears to sit among the Hyades from our viewpoint, but it is not actually a member. It lies at a different distance. This is a useful reminder that the night sky is a flat-looking projection of a three-dimensional universe. Two stars can appear side by side while being separated by enormous distances. A real cluster is not defined simply because its stars look close together from Earth. Astronomers determine membership using distance, motion, chemical composition, and other measurements. The European Space Agency's Gaia mission has been particularly powerful in this area because it has measured positions, distances, and motions for enormous numbers of stars with extraordinary precision. With data like this, astronomers can watch stellar groups reveal themselves through shared motion. Stars that were born together often travel through the galaxy in related ways, even after the original cluster has begun breaking apart. A cluster can therefore leave behind long streams or extended groups of stars that still preserve part of their common history. Open clusters are useful astronomical laboratories because their stars generally formed at around the same time from the same original cloud. That means the stars begin with similar ages and broadly similar chemical compositions, while having different masses. This gives astronomers a wonderful opportunity. If you want to understand how stellar mass affects stellar evolution, a cluster gives you many stars whose ages are approximately known and shared. It is the astronomical equivalent of studying a large family where everyone was somehow born on the same afternoon. Admittedly, family gatherings would become complicated. Mass determines how quickly a star evolves. Massive stars consume their nuclear fuel much faster than smaller stars. In a young cluster, you can still find very massive bright stars on the main sequence. In an older cluster, those same types of stars have already exhausted their core hydrogen and moved into later stages of evolution or died entirely. Astronomers can plot the brightness and colour of the stars in a cluster on a diagram and look for the point where stars begin leaving the main sequence. This main sequence turn-off provides one of the most useful ways of estimating the cluster's age. The basic principle is straightforward. If the very massive stars are still present and behaving like normal main sequence stars, the cluster must be young. If only lower mass stars remain on the main sequence, while the more massive members have already evolved, the cluster is older. Stars become clocks, not individually perfect clocks, but as a population, remarkably useful ones. Open clusters also help astronomers test models of stellar evolution, estimate distances, and examine how stars interact with their surroundings. But open clusters do not usually remain intact forever. The Milky Way is not a gentle environment. A cluster orbiting through the galactic disk can pass near giant molecular clouds. The gravity of those clouds can disturb the cluster. The overall gravitational field of the galaxy also exerts tidal forces. Individual stars within the cluster exchange energy through repeated gravitational encounters. Over enough time, some members gain enough energy to escape. This gradual loss is sometimes called evaporation. Not because stars literally boil away, although that would certainly make telescopes more exciting. Instead, repeated gravitational interactions slowly send some stars beyond the cluster's ability to hold them. The cluster becomes less massive. Its gravitational grip weakens. More stars escape. Eventually, many open clusters dissolve into the general disk of the galaxy. Our Sun's birth cluster probably met some version of this fate. Globular clusters are another matter. If open clusters resemble loose gatherings, globular clusters are much denser and more massive. A typical globular cluster contains hundreds of thousands of stars. Some contain more than 1 million. They are roughly spherical because their stars orbit in many different directions around the cluster's centre rather than occupying a thin disk. Through a telescope, a globular cluster can appear as an almost solid concentration of light at its centre, becoming progressively less crowded toward the edges. That light is not one object. It is an enormous population of individual stars. Globular clusters are also very old. Many formed more than 10 billion years ago, when the universe and the Milky Way were much younger. Because of this, they contain some of the oldest stars astronomers can study in our galaxy. They are not usually found only in the Milky Way's thin disk. Instead, many orbit within the much larger, roughly spherical halo surrounding the galaxy. If you could somehow look at the Milky Way from far outside and make its globular clusters brightly visible, you would see them scattered around the galaxy rather than confined to the luminous spiral disk. This distribution played an important role in understanding the shape and scale of the Milky Way. In the early 20th century, astronomer Harlow Shapley studied globular clusters and realized that they were not distributed evenly around Earth. Their arrangement suggested that the centre of the Milky Way was far away in the direction of Sagittarius. This helped move the Sun from any imagined position of galactic importance. We are not at the centre of the solar system. Earth orbits the Sun. The Sun is not at the centre of the Milky Way. The Milky Way is not at the centre of the universe. Astronomy has been remarkably consistent about this. Whenever humans place ourselves at the centre of something enormous, the universe tends to send revised seating arrangements. Globular clusters are fascinating partly because their interiors are so crowded. Near the centre of a dense globular cluster, the average distance between stars can be much smaller than in the Sun's neighbourhood. If our solar system were placed in such an environment, nearby stars might be dramatically brighter in the night sky. You could potentially have many stars bright enough to cast noticeable light. The sky would look beautiful. The gravitational environment, however, would require more consideration. Close stellar encounters would be more common. A passing star could disturb the distant regions of a planetary system. Over long periods, planets with very wide orbits might be vulnerable to disruption. That does not necessarily mean planets cannot exist in globular clusters. Astronomers have detected planets in some cluster environments, and planetary formation appears capable of producing surprises almost wherever we look. But a dense cluster is a more gravitationally active place than the relatively quiet region occupied by the Sun. The stars themselves also interact in ways that are rare in our neighbourhood. Normally, two isolated stars can pass one another and simply continue on altered trajectories. But in dense cluster cores, binary systems become especially important. A binary star has an internal store of orbital energy. When another star passes close to the pair, gravitational interactions can exchange energy between the objects. The binary may become tighter. The passing star may be accelerated. In some cases, stars can be thrown outward at high speeds. These interactions influence the structure and long-term survival of the cluster. Dense environments can also increase the chance of stellar collisions or near collisions. Stars are extremely small compared with the distances between them, so direct impacts are still not everyday events. Even a crowded star cluster contains a great deal of empty space, but compared with the solar neighbourhood, the probability increases substantially. This can produce unusual stars. One interesting example is the blue straggler. In an old cluster, the most massive ordinary stars should already have evolved away from the main sequence. Yet astronomers sometimes find stars that appear hotter, bluer, and younger than expected. They seem to have missed the memo about the cluster's age. These are blue stragglers. The leading explanations involve interactions such as mergers between stars or the transfer of material in binary systems. A star that gains fresh mass can effectively behave like a more massive, younger-looking star. It has not actually travelled backward in time. It has simply acquired new material and confused anyone looking at the diagram. Globular clusters can also undergo a process called mass segregation. Through repeated gravitational encounters, more massive stars tend to lose kinetic energy and settle toward the centre, while lower mass stars can gain energy and move outward. Over long timescales, this changes the distribution of stars within the cluster. The core becomes more concentrated with heavier objects. Neutron stars and stellar mass black holes can participate in this process as well. This raises an interesting question about what may exist in the centres of some clusters. Astronomers have investigated whether certain globular clusters might contain intermediate mass black holes. These would be more massive than the black holes produced by individual stars, but much less massive than the supermassive black holes found at the centres of large galaxies. Evidence for such objects has been debated, and confirming them is difficult. A black hole in a dense cluster does not politely illuminate itself for observation. Astronomers have to infer its presence from the motion of surrounding stars, radiation from nearby material, gravitational wave events, or other indirect evidence. This is another recurring habit in astronomy. Much of the universe refuses to introduce itself directly. We study what visible things do and work backward. Globular clusters also contain clues to the early history of galaxies. Their stars generally contain lower proportions of heavy elements than younger stars like the Sun. Astronomers call elements heavier than hydrogen and helium metals, which can be confusing if your chemistry teacher spent years insisting that oxygen is not a metal. Astronomy has chosen a broader definition and seems comfortable with it. A star's metallicity tells us something about the material from which it formed. The first generations of stars formed mostly from hydrogen and helium created in the early universe. As stars lived and died, they produced heavier elements and released them into space. Later generations of stars formed from increasingly enriched material. Because many globular clusters are ancient, their chemical compositions preserve information about earlier stages of galactic history. The picture is more complicated than scientists once thought. Globular clusters were previously treated as simple stellar populations, with all their stars sharing essentially one age and one chemical composition. Detailed observations have revealed that many globular clusters contain multiple stellar populations, with measurable differences in certain chemical abundances. That means their formation histories may have been more complicated. Some may have experienced multiple episodes of star formation or internal chemical enrichment. Others may preserve evidence of environments quite different from simple one-time collapses. In some cases, Astronomers even debate whether an unusually large cluster could be the remaining nucleus of a small galaxy that was stripped apart by the Milky Way. Omega Centauri is a famous example. It is the largest and among the most unusual globular clusters associated with our galaxy. Its stars show a range of chemical compositions that suggest a more complicated history than a typical cluster. One possibility is that Omega Centauri represents the dense central remnant of a dwarf galaxy whose outer stars were removed through interactions with the Milky Way. If that interpretation is correct, then our tidy categories begin overlapping again. Is it a cluster? Is it the remains of a galaxy? The answer may be that its history matters more than the label. Cosmic structures are not manufactured according to a catalogue. They grow, merge, lose material, and change identity. Something that begins as the centre of a small galaxy can later resemble an enormous star cluster. Something that begins as a young cluster can gradually dissolve until its members are indistinguishable from surrounding stars. Astronomers therefore study not only what a structure looks like today, but how it may have arrived there. The Milky Way contains many open and globular clusters, but other galaxies have their own populations. Large elliptical galaxies can host thousands of globular clusters. Galaxy mergers can alter cluster systems. Young massive clusters can form during intense episodes of star formation. Some compact young clusters contain enough stars that astronomers wonder whether they may eventually evolve into objects resembling globular clusters. Studying clusters in other galaxies gives researchers another way to reconstruct galactic histories. If one galaxy has several populations of globular clusters with different chemical properties, those groups may reflect different phases of formation or past mergers. A galaxy can effectively carry fossils of its construction history in the clusters orbiting around it. The same principle works on smaller scales. A cluster contains information about the cloud that formed it, the ages of its stars, their compositions, their motions, and the fraction of stars found in binary systems all preserve clues about the original environment. Young clusters are especially valuable because some have not yet moved far from their birthplace. Around them, astronomers can still find gas and dust left from the star-forming region. Newly formed stars may possess protoplanetary disks. These disks contain the material from which planetary systems can develop. That means clusters connect our first two levels of structure directly. A large cloud forms a group of stars. Individual stars develop disks. Planets form inside those disks. The cluster evolves. Some stars remain together. Others depart, taking their planetary systems with them. Billions of years later, one of those stars may look completely isolated, even though it began life in a crowded stellar nursery. Our Sun may be exactly such a case. There are clues suggesting that the Sun formed in an environment containing other stars, possibly including massive ones. Certain short-lived radioactive isotopes present in primitive solar system material may have been supplied or influenced by nearby massive stellar activity, although the exact birth environment remains an active area of research. Whatever the details, the Sun almost certainly did not emerge from a perfectly solitary little cloud with a sign on the door requesting privacy. Star formation tends to happen where there is enough gas to produce more than one star. That observation brings us toward the material surrounding many young clusters. When we look at places where stars are forming today, we often see spectacular clouds of glowing gas and dark dust. The Orion Nebula is one familiar example. At its heart is a young cluster known as the trapezium, containing hot massive stars whose radiation illuminates and reshapes the surrounding gas. Those stars are young enough that we can watch the environment from which they formed being transformed around them. Ultraviolet radiation ionizes gas. Stellar winds carve cavities. Dense pockets continue collapsing. Protoplanetary disks are exposed to intense radiation. Birth and disruption happen together. A star-forming region is not a quiet factory where one object is completed before the next begins. Different processes overlap. Some stars have already formed. Others are still gathering material. Elsewhere, gravity is only beginning to compress a dense clump. Massive young stars may start destroying the same cloud that created them before slower forming objects have finished developing. This feedback helps determine how efficiently a cloud turns its gas into stars. It can halt star formation in some places while possibly compressing gas and encouraging collapse in others. A cluster is therefore not merely a collection of stars that happens to occupy one location. It is part of a larger cycle involving interstellar material. Gas becomes stars. Stars alter the gas. Some stars explode and return enriched material. The remains mix with the interstellar medium. Later clouds form from that material. New clusters appear. Planetary systems emerge within them. The cycle repeats, although never in exactly the same way. If you look at an old globular cluster, most of the gas associated with its original star formation is long gone. What remains is primarily the stellar population. Look at a very young cluster, and the birth environment may still be obvious. Dust can obscure newborn stars in visible light. Infrared telescopes are particularly useful because infrared radiation can pass through some of that dust more effectively, revealing stars hidden inside. Radio telescopes can map cold molecular gas. X-ray observations can identify energetic young stars. Different wavelengths reveal different components of the same region. A beautiful visible light nebula is only one part of the story. Behind the glowing colours may be cold, dark material that contains the next generation of stars. Some of the most important star-forming structures are almost invisible to human eyes. They are giant molecular clouds. These clouds can contain tens of thousands, hundreds of thousands, or even millions of times the mass of the Sun in gas. Most of that gas is molecular hydrogen, accompanied by helium, trace molecules, and dust. Temperatures can be only a few tens of degrees above absolute zero. That cold temperature matters. Hot gas has fast-moving particles that resist collapse more effectively. Cold gas can settle into dense structures where gravity becomes increasingly important. Within those enormous clouds are filaments, clumps, and dense cores. Some of those cores become stars. Some produce multiple stars. Clusters emerge from especially active regions. Cold gas is where the next stage of the story begins. If star clusters are cities of suns, then giant molecular clouds are the raw landscapes from which those cities are built. They are enormous concentrations of gas and dust drifting through galaxies, often extending across tens or even hundreds of light years, and containing enough material to form thousands, sometimes millions of stars. At first glance, that may sound like a very crowded place. In reality, even these clouds are extraordinarily thin by everyday standards. A giant molecular cloud is much denser than the ordinary interstellar medium around it, but it's still far closer to a vacuum than anything we would call a cloud on Earth. If you could somehow place yourself inside one without the considerable inconvenience of freezing, suffocating, and being several thousand light years from the nearest decent cup of tea, you would not necessarily see thick fog surrounding you. Space remains very empty. The remarkable thing is not that molecular clouds are dense in an everyday sense. It is that they are dense enough, over enormous distances, for gravity to begin taking control. Most of the material inside a giant molecular cloud is hydrogen. Hydrogen is by far the most abundant element in the universe, and in sufficiently cold shielded regions, hydrogen atoms can pair up to form molecular hydrogen. That is where the name comes from. These clouds also contain helium, small amounts of heavier elements, more complicated molecules, and tiny solid particles collectively known as interstellar dust. The word dust makes this material sound rather domestic. It is not simply the cosmic equivalent of whatever is accumulating behind a bookshelf. Interstellar dust consists of microscopic grains containing materials such as silicates, carbon-rich compounds, and ices. Individual grains are tiny, but their effect on astronomy is substantial. Dust absorbs and scatters visible light. That is why some regions of the Milky Way look dark even though there are stars behind them. The darkness is not necessarily an absence of stars. Sometimes it is a curtain. A thick cloud of dust between us and distant stars can block their visible light so effectively that the cloud appears as a black shape against a brighter background. These are called dark nebulae. One of the most recognizable examples is the Horsehead Nebula in Orion. Its familiar shape appears because a dense cloud of dust blocks light from glowing gas behind it. The horse's head is therefore not a solid object. It is a silhouette. Our brains, naturally, have decided it looks like an animal. Give humans a large enough patch of interstellar matter, and we will eventually name it after a horse, crab, eagle, butterfly, cat, or something else that was not remotely involved in its formation. Nebula is a broad word. Historically, astronomers used it for fuzzy objects in the sky, before they knew what many of those objects really were. The word comes from Latin for cloud. For centuries, anything that looked misty through a telescope could be called a nebula. Some of those fuzzy objects turned out to be actual clouds of gas and dust within the Milky Way. Others turned out to be entire galaxies. The Andromeda Galaxy, for example, was once known as the Andromeda Nebula, before astronomers understood that it was a vast stellar system far beyond our own. Today, when astronomers speak of nebulae, they usually mean particular clouds or glowing regions of interstellar material. But not all nebulae are the same. Some are places where stars are forming. Others are created by stars near the ends of their lives. Some glow because nearby stars energize their gas. Some shine by reflecting starlight. Others are mostly visible because they block whatever is behind them. So calling something a nebula tells you that gas or dust is involved. It does not yet tell you the full story. For our purposes, the most important nebulae are connected with stellar birth. A giant molecular cloud does not collapse evenly from one edge to the other. It contains structure. Turbulence moves through the gas. Magnetic fields influence charged particles. Shock waves pass through. Gravity pulls more strongly where matter is already slightly concentrated. The result is a cloud filled with smaller filaments, knots, clumps, and dense cores. Modern observations show that filaments are especially common in star-forming clouds. These long thread-like concentrations of gas can stretch for many light years. Where filaments intersect or become particularly dense, gravity may eventually overwhelm the forces resisting collapse. A dense core begins contracting. That core can become the birthplace of a star. The process is not instantaneous. Nothing in star formation appears particularly concerned with keeping a human schedule. A collapsing core may take hundreds of thousands of years to produce a protostar. The protostar is a young stellar object that has not yet settled into the stable, hydrogen-fusing stage we normally associate with a mature star. Material continues falling inward. As it collapses, it heats up. Because the original cloud had some rotation, the infalling material cannot all drop directly into the centre. Instead, much of it forms a rotating disk around the young star. This is the protoplanetary disk we encountered earlier. The star is forming at the centre. Potential planets are beginning their much slower construction project in the material around it. At the same time, the protostar can launch powerful outflows and narrow jets from its polar regions. These jets can blast through the surrounding cloud, creating glowing shocks where fast-moving material collides with gas. Astronomers call some of these small glowing patches Herbig-Haro objects. They can mark the activity of stars that are still hidden deeply within their birth clouds. The newborn star may be invisible in ordinary optical light because dust surrounds it, yet its jets announce that something energetic is happening inside. Infrared observations are particularly useful here. Dust that blocks visible light is more transparent at many infrared wavelengths. Infrared telescopes can therefore look into regions that appear dark to our eyes and reveal populations of young stars. This has changed our view of many famous nebulae. A glowing cloud that once looked like a smooth patch can become, in infrared, a complicated nursery filled with stars at different stages of formation. Some are already visible. Some remain wrapped in dusty envelopes. Some have disks. Some are still so young that astronomers identify them mainly from the way they heat nearby material. The Orion Molecular Cloud Complex is one of the best-known examples. Orion is familiar in the night sky because its bright stars make a distinctive pattern. Within the same general direction lies an enormous region of gas and dust where stars are actively forming. The Orion Nebula is only one illuminated portion of that much larger complex. It lies roughly 1,300 light-years from Earth and is one of the nearest major star-forming regions containing massive stars. To the unaided eye under dark skies, the Orion Nebula appears as a fuzzy patch in Orion's sword. Through a telescope, it becomes far more detailed. Bright gas spreads around a central region containing the Trapezium cluster, a group of young stars including several hot, massive members. These stars flood the surrounding gas with ultraviolet radiation. That radiation strips electrons from hydrogen atoms. The gas becomes ionized. When electrons recombine with atoms and energy is released, the nebula glows. This type of glowing region is called an emission nebula. The familiar reddish colours seen in many astronomical images often come from hydrogen emission, although telescope images may combine multiple wavelengths and use colour to represent different gases or physical conditions. The Trapezium's massive stars are therefore doing two things at once. They are illuminating their surroundings beautifully, and they are destroying them. Ultraviolet radiation heats and disperses gas. Stellar winds push material outward. The same cloud that gave birth to the stars is gradually being eroded by them. This is one of the strange features of star formation. The most massive newborn stars can help shut down further star formation in their immediate surroundings. They arrive, shine with enormous intensity, and begin demolishing the nursery. Rather inconsiderate, really. Smaller stars may spend millions or billions of years quietly shining. A massive young star can alter an entire region almost immediately by astronomical standards. That feedback helps shape molecular clouds. It creates cavities. It compresses gas into ridges. It exposes young stars that were previously hidden, and in some cases the compression may trigger new collapse in neighbouring regions. This leads to a complicated relationship between stellar feedback and star formation. A massive star can disperse gas in one location while compressing it in another. An expanding bubble may squeeze nearby material until parts of it become gravitationally unstable. Then new stars begin forming around the edges. The nursery can partly destroy itself and partly encourage another generation. Supernova explosions add still more energy. When a massive star reaches the end of its life and explodes, the blast wave travels into the surrounding interstellar medium. That shock can clear enormous cavities. It can stir gas. It can compress dense clouds, and it spreads newly produced elements outward. A molecular cloud therefore does not exist in isolation. It lives within the active environment of a galaxy. Nearby stars heat it. Supernovae disturb it. Galactic rotation stretches it. Magnetic fields thread through it. Gravity continuously tries to pull denser regions inward. The balance between those processes determines when and where stars appear. Despite the enormous masses of giant molecular clouds, star formation is surprisingly inefficient. Only a fraction of the available gas is converted into stars before feedback and other effects disperse the cloud. If gravity were allowed to collapse all the gas freely and rapidly, galaxies like the Milky Way would produce stars much faster than they actually do. Something is slowing the process. Turbulence helps. Magnetic fields help. Stellar feedback helps. The details remain an active field of research because giant molecular clouds are complicated systems rather than simple balls of gas waiting politely to collapse. That complexity is visible in regions such as the Eagle Nebula. The Eagle Nebula became especially famous because of the structures known as the Pillars of Creation. They are tall columns of gas and dust photographed in remarkable detail by the Hubble Space Telescope, and later observed by the James Webb Space Telescope at infrared wavelengths. The pillars look solid in photographs. They are not. They are enormous concentrations of gas extending across light years. radiation from nearby massive stars is eroding their outer surfaces. Dense pockets within them can contain forming stars. The striking shapes exist partly because less dense material has been removed more quickly, leaving denser columns behind. We are essentially seeing erosion on a cosmic scale. Instead of wind and rain shaping rock, ultraviolet radiation and stellar winds shape gas. The timescales are very different. So is the landscaping budget. Another famous star-forming region is the Carina Nebula. It contains some of the most massive and luminous stars in the Milky Way, along with enormous clouds, cavities, pillars, and young stellar groups. One of its best-known inhabitants is Eta Carinae, an extremely massive and unstable stellar system that has undergone dramatic eruptions. Regions like Carina make clear that a cosmic nursery is not necessarily peaceful. The phrase sounds gentle. The reality can involve intense radiation, supersonic outflows, gravitational collapse, stellar winds, and eventually supernovae. Birth in the universe can be noisy. We simply cannot hear it because sound waves do not travel through the near vacuum between stars to reach us. Space maintains a rather misleading silence. Not every nebula is powered by the birth of stars. Some are illuminated more gently. Reflection. Nebulae shine because dust scatters light from nearby stars. They often appear blue in visible light images because small dust grains scatter shorter wavelengths of visible light more effectively. The blue haze around some stars in the Pleiades is a familiar example. The stars are passing through or near dusty material that reflects their light. This does not necessarily mean the dust is leftover material from the cluster's formation. The cluster can simply be moving through a dusty region. Reflection nebulae are therefore visible not because their gas is strongly ionized, but because nearby starlight is bouncing toward us. Then there are planetary nebulae. The name is deeply unhelpful. Planetary nebulae have essentially nothing to do with planets. They received the name because some early telescopic observers thought their round appearances resembled the disks of planets. A planetary nebula forms when a star similar in mass to the Sun reaches a late stage of its life and sheds its outer layers. The exposed hot core illuminates the expanding gas. These nebulae can have beautiful rings, shells, lobes, and complicated shapes. Eventually the gas disperses into interstellar space, while the stellar core becomes a white dwarf. Supernova remnants come from a much more violent process. When certain stars explode, or when particular white dwarf systems undergo thermonuclear explosions, rapidly expanding debris interacts with surrounding gas. The result can be a complex glowing structure filled with shock-heated material, magnetic fields, and accelerated particles. The Crab Nebula is one famous supernova remnant. Its explosion was observed from Earth in the year 1054. At its centre is a neutron star spinning rapidly and producing regular pulses of radiation. So when we look around a galaxy and see different nebulae, we're often looking at different stages in the recycling of matter. A molecular cloud collapses. Stars form. Stars live. Some shed material gradually. Others explode. Gas and heavier elements return to interstellar space. That material mixes. New clouds form, new stars appear, the atoms are reused. This recycling is essential because the early universe contained almost entirely hydrogen and helium, with only tiny amounts of a few other light elements. The carbon, oxygen, silicon, iron, and many other heavier elements found in planets were produced later through stellar processes. Stars manufactured many of those elements. Stellar deaths distributed them. Clouds incorporated them. Planetary systems formed from enriched material. The universe, therefore, became chemically more complicated as generations of stars lived and died. A molecular cloud forming stars today is not made from pristine material left untouched since the beginning. Much of its gas has a history. Atoms in that cloud may have passed through earlier stars. Dust grains may contain material created in stellar atmospheres or explosions. The ingredients for future planets can already include the products of ancient stars. that make star-forming clouds both beginnings and continuations. They create new objects from old material. The cycle also changes the appearance of galaxies. Spiral galaxies like the Milky Way contain substantial amounts of gas and dust, especially in their disks. Spiral arms often appear bright because they contain young stars, glowing nebulae, and regions of active star formation. The spiral arms are not rigid collections of exactly the same stars permanently travelling together like spokes on a wheel. Stars and gas move through the galaxy, while the spiral pattern can be maintained through more complicated gravitational and dynamical processes. As gas enters dense regions associated with spiral structure, it may be compressed. Molecular clouds form or become denser. Star formation increases. Young massive stars then illuminate the area, making spiral arms especially noticeable. This means the glowing arms of a galaxy are partly signposts for recent star formation. Blue stars do not live very long. If we see them concentrated in a region, they must have formed relatively recently. Likewise, bright emission nebulae tell us that hot young stars are nearby. A galaxy can therefore reveal where it is actively making new stars simply through its colour and structure. Some galaxies form stars slowly, others experience intense bursts. A starburst galaxy may produce stars at a rate far above that of the Milky Way. Such activity can be triggered by interactions or mergers between galaxies. Gravity disturbs gas. Clouds collide. Material is driven toward dense regions. Star formation accelerates. Once again, a structure at one scale influences structures at another. Two galaxies interact. Their molecular clouds respond. Stars form. Clusters appear. Planetary systems may eventually develop around some of those stars. The cosmic hierarchy is not merely a set of boxes nested neatly inside one another. The levels affect each other. A galaxy shapes the environment in which clouds exist. Clouds create stars. Stars reshape clouds. Stars gather into clusters. Clusters move through galaxies. Everything is connected by gravity, radiation, motion, and the recycling of matter. Even the largest molecular clouds do not last forever. Over tens of millions of years they are altered and dispersed. Star formation consumes some material. Radiation removes more. Winds and supernovae push gas outward. Galactic forces pull structures apart. Eventually, the original cloud may no longer exist as a recognizable object. But its material has not simply vanished. Some is locked inside stars and planets. Some returns to more diffuse interstellar gas. Some may later gather into another cloud elsewhere. The nursery closes, the children leave, and several million years later, cosmic estate agents are presumably discussing redevelopment. The stars formed from one molecular cloud do not necessarily remain near one another either. A bound cluster may survive. A loose association may disperse. Individual stars move away carrying their planetary systems. Massive stars may already have died before the slower process of dispersal is complete. A star-forming region can therefore change dramatically over a relatively short astronomical interval. If we could watch the Orion Nebula in fast-forward across several million years, the familiar glowing cloud would not remain. Gas would disperse. Young stars would separate into different trajectories. Some would remain together longer than others. The bright nebula would fade. Eventually the region would become much less recognizable. This is worth remembering whenever we see astronomical photographs. We tend to experience them as static images. The universe is not static. The Horsehead Nebula is changing. The pillars of creation are changing. The Orion Nebula is changing. Molecular clouds are collapsing and dispersing. Stars move. Shock fronts expand. Radiation erodes gas. We see one moment because our lives are too short to watch most of the transformation directly. Astronomers solve this partly by looking at many different regions. One cloud may show very early collapse. Another contains embedded protostars. Another has young stars emerging from their dusty surroundings. Another has already been carved apart by massive stellar radiation. Put those regions together and we can reconstruct an approximate sequence. It is like understanding a forest by examining many trees of different ages rather than waiting several centuries beside one seed. Viewing a galaxy from the inside is a slightly inconvenient way to understand its shape. Imagine trying to describe an entire forest while standing halfway between two trees. You can see trunks, branches, patches of sky, and perhaps a squirrel making questionable decisions. But the overall structure is difficult to judge because you are part of it. That is roughly our situation with the Milky Way. We live inside its disk, surrounded by its stars, gas, dust, and dark matter, so the bright band stretching across a dark sky is not the galaxy seen from outside. It is our view through the crowded plane of the galaxy itself. When you look toward that band, you're looking through a much greater concentration of distant stars than when you look above or below the galactic disk. Most are too far away to distinguish individually with the unaided eye. Their combined light produces the pale, milky glow that gave our galaxy its name. For a very long time, humans had no idea that this band represented the interior of an enormous stellar system. It was simply part of the sky. Only gradually did telescopes reveal that the Milky Way contained vast numbers of stars. Even then, another question remained. Was the Milky Way the entire universe? For centuries, astronomers debated whether the fuzzy spiral objects seen through telescopes were small structures inside our galaxy or enormous systems far beyond it. The answer changed our sense of scale dramatically. Those objects were other galaxies. The Milky Way was not the universe. It was one galaxy among an enormous population. Our local cosmic address had just acquired a much larger neighbourhood. A galaxy is, in the simplest terms, a gravitationally organised system containing stars, stellar remnants, gas, dust, and dark matter. That definition sounds tidy. Real galaxies are not always tidy. Some have elegant spiral arms, some are smooth and rounded, some look stretched, distorted, or lopsided. Some are tiny compared with the Milky Way. Others are much larger. Some are actively producing new stars. Others have very little cold gas and almost no ongoing star formation. Some contain brilliant central regions powered by matter falling towards supermassive black holes. Others are faint enough that finding them requires patient observations and extremely sensitive instruments. There is no single standard galaxy. The Milky Way is a useful example, but it is not the template from which every other galaxy was copied. Our galaxy is a barred spiral. That means it has a flattened rotating disk, spiral structure, and an elongated bar of stars crossing its central region. The Sun sits in the disk, far from the centre, roughly within a smaller feature often called the Orion spur or local arm. From here we orbit the galactic centre along with billions of other stars. One journey around the Milky Way takes the Sun on the order of a couple 100 million years. The last time the solar system was in approximately the same part of its galactic orbit, dinosaurs were still a major concern for anything trying not to be eaten. One galactic year is therefore not especially useful for scheduling birthdays. The visible disk of the Milky Way extends for roughly 100,000 light-years, depending on exactly what one chooses to measure. Its full stellar and dark matter structures extend farther, and just as the solar system does not end neatly at Neptune, the Milky Way does not have a simple glowing edge where everything suddenly stops. The bright disk fades. A much more diffuse stellar halo surrounds it. Globular clusters orbit in this larger region. Far beyond the visible stars, a huge halo of dark matter is thought to extend around the galaxy. Most of the galaxy's mass may be in this invisible component. That fact becomes clear when astronomers examine how stars and gas orbit. If most of the mass in a spiral galaxy were concentrated only where the visible matter is found, stars farther from the centre should orbit much more slowly than they do. Instead, measured rotation curves remain unexpectedly flat over large distances. The outer stars are moving too quickly for the gravity of the visible stars and gas alone to hold them in their observed orbits. Something else contributes mass. That unseen matter is one of the strongest lines of evidence for dark matter. It does not glow. It does not create the beautiful spiral arms that dominate photographs. Yet gravitationally it is essential. A galaxy is therefore much larger in mass than its visible appearance suggests. The part that makes the photograph is only part of the structure. Within the disk, the spiral arms are among the most recognizable features. They contain many young bright stars, star-forming regions, molecular clouds, and glowing nebulae. Because massive blue stars are extremely luminous and live for relatively short periods, their presence makes spiral arms particularly noticeable. Older stars also exist throughout the disk, including between the arms. The spiral pattern is not simply a set of permanently fixed lanes containing the same stars forever. Stars orbit through the galaxy. Gas flows. Patterns can be influenced by density waves, gravitational interactions, bars, and other processes. The exact formation and persistence of spiral structure is a complicated subject, and different galaxies may not produce their arms in exactly the same way. Some have two prominent arms, others have many fragmented arms. Some look almost fluffy, with broken spiral pieces spread throughout the disk. Astronomers call these flocculent spirals. Apparently even galaxies are allowed to have untidy hair. At the centre of the Milky Way is a dense region called the galactic bulge. Embedded within the central area is a supermassive black hole known as Sagittarius A star. Its mass is about 4 million times that of the Sun. That sounds enormous until we compare it with the central black holes in some other galaxies, which can reach billions of solar masses. Sagittarius A star does not swallow the entire Milky Way. A common image of a black hole is something like a cosmic vacuum cleaner pulling everything relentlessly inward. Gravity does not work that way. If the Sun could somehow be replaced by a black hole with exactly the same mass, Earth would continue orbiting at essentially the same distance. We would have several other problems, most notably the sudden absence of sunlight, but being immediately sucked inward would not be one of them. The black hole at the galactic centre has an enormous gravitational influence nearby, but stars far out in the disk orbit mainly in response to the combined mass distribution of the galaxy. Near Sagittarius, a star, astronomers have tracked individual stars moving around the invisible central object. Some complete highly elongated orbits at extraordinary speeds. Their motion provides direct evidence for the immense mass concentrated there. This region is obscured from us in visible light by large amounts of dust in the galactic plane, so astronomers often study it using infrared, radio, X-ray and other observations. Once again, different wavelengths allow us to see different parts of the same structure. Visible light photographs show one galaxy. Radio observations reveal cold gas and magnetic features. Infrared can penetrate dust and highlight cooler stars or warm dust. Ultraviolet emphasizes hot young stars. X-rays reveal energetic sources such as hot gas, compact stellar remnants, and material near black holes. A galaxy is not one picture. It is a layered physical system. Move beyond spiral galaxies, and the variety becomes even clearer. Elliptical galaxies generally have smoother, rounder or more elongated shapes, without the obvious spiral arms of galaxies like the Milky Way. They can range from relatively small systems to enormous giant ellipticals containing vast stellar populations. Many large elliptical galaxies are dominated by older stars and contain comparatively little cold gas. Without large supplies of cold gas, they form relatively few new stars. That gives them a redder overall appearance than actively star-forming spiral galaxies, because short-lived blue stars are no longer being produced in large numbers. The stars in an elliptical galaxy also move differently from those in a thin spiral disk. In a spiral galaxy, much of the stellar population participates in organized rotation around the center. An elliptical system is more like an enormous swarm. Stars travel on many different kinds of orbits and in different directions. The galaxy remains gravitationally bound, but its structure is supported more by the random motions of its stars than by a thin, rotating disk. Large elliptical galaxies are often associated with dense galaxy environments. Some appear to have grown through repeated mergers. When galaxies collide and merge, their stars almost never crash directly into one another because the distances between stars are enormous compared with the sizes of the stars themselves. Two galaxies can pass through each other while most individual stars avoid physical collisions. The gravitational consequences, however, are dramatic. Orbits are rearranged. Gas clouds can collide and compress. Tidal forces stretch stars and gas into long tails. Central black holes may eventually move toward one another. New bursts of star formation can occur. After enough time, the original orderly disks may be transformed into a more rounded remnant. So a galaxy collision is both less and more violent than the word collision suggests. Individual stars mostly miss. The galaxies themselves are completely reorganized. The Milky Way and Andromeda are expected to experience a major interaction in the distant future. Andromeda is currently approaching our galaxy. Over billions of years, the two systems are likely to pass through one another and interact gravitationally, eventually producing a merged system. The night sky during some stages would be extraordinary. Andromeda could appear enormous as it approached. Long tidal structures might stretch across the sky. Stars would be redistributed. The solar system's position within the final remnant could change. But Earth, if it still existed in anything resembling its current form by then, would not necessarily be struck by another star. The odds of direct stellar collision remain extremely small. The larger concern for any distant future observers would probably be that the Sun itself will have changed substantially on comparable timescales. Astronomy has an irritating habit of scheduling multiple major events for dates long after anyone can complain. Between the familiar spiral and elliptical categories are lenticular galaxies. These have a disk and a central bulge but little obvious spiral structure. They often contain less cold gas and less star formation than typical spirals. They can look somewhat like spiral galaxies that have misplaced their arms. Then there are irregular galaxies. These resist simple classification. Some have been distorted by gravitational interactions. Others are naturally asymmetric or chaotic in appearance. The large and small Magellanic Clouds, satellite galaxies of the Milky Way, are nearby examples with irregular structures. They can be seen from much of the southern hemisphere as cloudy patches in the night sky. They are galaxies close enough to be obvious to the unaided eye under good conditions, although for most of human history their true nature was unknown. Dwarf galaxies form another crucial part of the galactic population. The word dwarf can make them sound insignificant. They are not. Dwarf galaxies are smaller and less massive than systems such as the Milky Way, but they are extremely common. Some contain billions of stars, others contain far fewer. They come in different forms, including dwarf spheroidal, dwarf elliptical, dwarf irregular, and small disk-like systems. The Milky Way is surrounded by numerous dwarf satellite galaxies. Some orbit nearby, some are being tidally disturbed, some are gradually losing stars to the Milky Way. Streams of stars spread around our galaxy as evidence of past and ongoing interactions. This is an important part of how large galaxies grow. Galaxies do not necessarily form once and then remain unchanged for the rest of cosmic history. They assemble, they accrete gas, they form stars, they merge with smaller galaxies. Sometimes they merge with comparable galaxies, they lose material, their star formation rises and falls, their central black holes become active and then quiet. A present-day galaxy is the result of its history. The Milky Way itself carries evidence of past mergers. Some stars in its halo move in patterns suggesting they came from smaller galaxies absorbed long ago. Chemical compositions reveal populations with different origins. Stellar streams trace disrupted satellites. Rather than one perfectly isolated system formed all at once, our galaxy appears to have grown partly by incorporating smaller systems. The process resembles construction by recycling entire buildings, a little dramatic for urban planning, but effective on galactic scales. Gas arriving from outside a galaxy can also support new star formation. Cold material may flow inward from the surrounding environment. Smaller gas-rich galaxies can contribute additional fuel during mergers. Inside the galaxy, gas circulates through the interstellar medium as stars form and die. Heavy elements accumulate over generations. The entire system evolves chemically as well as structurally. Galaxies in the early universe often looked different from mature galaxies nearby. Because light takes time to reach us, looking billions of light years away allows astronomers to observe galaxies at earlier stages of cosmic history. Many distant young galaxies are smaller, clumpier, and more actively forming stars. Mergers were more common when the universe was denser. Over billions of years, small systems combined into larger ones. Disks developed, bulges grew, black holes gained mass, galactic structures became increasingly varied. This process is sometimes described as hierarchical galaxy formation. Small structures form and combine into larger ones. Dark matter halos grow through mergers. Ordinary gas falls into them. Stars form. Galaxies assemble within the underlying dark matter framework. This returns us to an important distinction. The luminous galaxy we photograph is not the whole gravitational structure. A dark matter halo surrounds it and helps guide its growth. Smaller halos can merge into larger halos. The galaxies may eventually merge as well, although not necessarily immediately. This is one reason galaxies naturally become linked to the next scale of structure. A galaxy rarely exists in complete isolation. Even objects that look alone may inhabit the outskirts of larger dark matter environments, or have faint companions that are difficult to detect. The Milky Way certainly is not alone. It has dozens of known satellite galaxies, and searches continue to reveal extremely faint dwarf systems. Many are dominated gravitationally by dark matter. Some contain so few stars that they are nearly invisible against the foreground population of the Milky Way. Astronomers identify them through subtle concentrations and shared motions. These tiny galaxies are scientifically valuable because they can test ideas about dark matter, galaxy formation, and the number of small halos predicted by cosmological models. At the opposite end of brightness are galaxies powered by active galactic nuclei. Most large galaxies are thought to contain supermassive black holes at their centres. Usually, as with Sagittarius A star, the black hole may be relatively quiet. But if large amounts of gas fall toward it, the situation changes. Matter does not usually drop straight into the black hole. It forms a hot, rotating accretion disk. Friction and magnetic processes heat the material to extraordinary temperatures. The region can release enormous amounts of radiation. In some systems, narrow jets of particles are launched outward at speeds close to that of light. An active galaxy can therefore shine intensely from a region much smaller than the galaxy around it. Quasars are among the most luminous examples. Some are visible across billions of light years. When quasars were first discovered, their enormous distances and energy outputs were difficult to understand. Today, they are recognized as active galactic nuclei powered by rapidly accreting supermassive black holes. This creates a wonderful piece of astronomical irony. A black hole itself emits no light from inside its event horizon, yet the material falling toward one can make its surroundings among the brightest places in the universe. The darkness is capable of putting on quite a show. Central black holes also appear to influence the galaxies around them. Energy released by an active galactic nucleus can heat or expel gas. That can reduce the supply of cold material available for new star formation. This process, called feedback, may help explain why some massive galaxies stop producing stars efficiently. Stellar feedback and black hole feedback therefore operate at different scales but participate in the same broader question. How does a galaxy regulate itself? If gas simply cooled and collapsed without interruption, many galaxies would make too many stars compared with what astronomers actually observe. Something limits that growth. Supernovae inject energy. Stellar winds move gas. Radiation heats material. Central black holes can drive enormous outflows. Galaxies are constantly balancing gravity, cooling, heating, inflow and outflow. They are not static containers filled with stars. They are active ecosystems of matter and energy. Even apparently quiet galaxies have long histories behind their calm appearance. Elliptical galaxies filled with old red stars may have experienced violent mergers billions of years ago. Spiral galaxies may have consumed smaller companions. Dwarf galaxies may have lost their gas while orbiting larger systems. A galaxy's current shape is a snapshot rather than a permanent identity, and shape itself is affected by environment. A galaxy drifting through a relatively empty region may evolve differently from one moving through a dense cluster. In crowded environments, galaxies pass near one another more often. They experience tidal forces. Hot gas surrounding the cluster can strip away their own gas. Interactions can trigger or suppress star formation. Small galaxies can be pulled apart. Large galaxies can grow by swallowing them. The surroundings matter. This becomes increasingly obvious when we map galaxies across the sky. They are not distributed evenly. Look at a large survey covering a broad region of the universe, and galaxies begin to form patterns. Some are isolated or nearly so. Others appear in pairs. Some gather in small collections. Elsewhere, hundreds or thousands occupy the same broad region. The Milky Way belongs to one of those smaller collections. Andromeda is part of it. The Triangulum galaxy is part of it. Numerous dwarf galaxies belong to it as well. Together these systems form what astronomers call the local group. The name sounds almost charmingly modest. A local group might be 6 people meeting once a month in a community hall. Our version extends across millions of light years and contains galaxies carrying hundreds of billions of stars. Within it, gravity connects the major members in a shared environment. The Milky Way has its satellites. Andromeda has its satellites. Smaller galaxies move between and around them. Some will merge, others may survive for very long periods. The entire system has its own dynamics beyond those of any individual galaxy. Once galaxies begin gathering this way, a new level of the cosmic hierarchy appears. The island analogy starts to fail, because these islands are not scattered randomly across an empty ocean. They have neighbours, they form families. Some families are small and relatively calm, others grow into much denser communities, where galaxies orbit through enormous reservoirs of hot gas and dark matter. The local group is a good place to begin because it is the larger cosmic family we actually belong to. Our galaxy, the Milky Way, is one of its dominant members. Andromeda is the other major galaxy. And the Triangulum galaxy is smaller but still substantial. Around them are dozens of dwarf galaxies, many of them faint, some stretched by gravity, some slowly losing stars, and some so difficult to detect that astronomers are still finding new members. The word group sounds modest, and compared with the larger structures we will eventually encounter, it is. But modest is a relative term when the family gathering contains several large galaxies, many smaller ones, vast amounts of dark matter, and a total extent measured in millions of light years. A galaxy group is generally a collection of galaxies that are close enough to be associated gravitationally. There is no single exact number of galaxies required before nature officially issues a membership card. Some groups contain only a few prominent galaxies, others contain dozens. What matters is that the galaxies share a common environment and are influenced by the gravity of the larger system. Groups are extremely common. In fact, many galaxies in the universe are found in groups rather than living entirely alone. The Milky Way is therefore not unusual in having neighbours. Its neighbourhood is simply the one we have had the most opportunity to study. The local group stretches across roughly 10 million light-years, depending on where one chooses to define its outer limits. That is already difficult to picture. Light leaving one side of the group could require millions of years to reach the other. And yet, from the perspective of large-scale cosmic structure, the whole arrangement is still relatively compact. Most of its visible mass is concentrated around the Milky Way and Andromeda, each of which has its own population of satellite galaxies. You can think of the system as two large subfamilies gradually interacting within a shared gravitational environment, with the Triangulum galaxy and many dwarfs joining the arrangement. Although perhaps do not think about it too much like an actual family gathering. Galaxies have a habit of merging with their relatives. This would make most holiday dinners considerably more alarming. The Milky Way and Andromeda are approaching each other. Their motion is not simply the general expansion of the universe carrying them apart. On this scale, their mutual gravitational attraction is strong enough to dominate. Over the next several billion years, they are expected to interact, pass through one another, and eventually merge into a larger galaxy. That future event is one of the clearest demonstrations that a galaxy group is not a static display. Its members move, they orbit, they fall toward one another. Smaller galaxies can be captured, satellites can be torn apart, gas can be stripped, stars can be scattered into enormous streams. A group evolves as a single environment even though its individual galaxies remain recognizable for long periods. The local group is already filled with evidence of that evolution. The Milky Way is surrounded by stellar streams that are thought to be remnants of smaller galaxies, or star clusters disrupted by our galaxy's gravity. The Sagittarius dwarf spheroidal galaxy is currently being pulled apart as it interacts with the Milky Way. Its stars form long streams wrapping through the galactic halo. The Magellanic Clouds are also interacting with our galaxy and with each other. A long structure known as the Magellanic Stream contains gas extending across a large part of the sky, evidence of gravitational interactions and the complex movement of material among these nearby systems. From Earth, none of this looks especially dramatic. The stars do not visibly rush across the sky. The galaxies do not collide between one bedtime and the next. The process unfolds over hundreds of millions or billions of years. Astronomy remains committed to making its most impressive events extremely difficult to watch in real time. Fortunately, different galaxy groups let us see different stages of similar processes. Some contain galaxies that are widely separated, others contain close pairs. Some show obvious tidal tails created by gravitational encounters. Some contain galaxies in the middle of mergers. By studying many systems, astronomers can reconstruct how groups change. The same trick we used with star formation works again. Instead of waiting billions of years for one group to evolve, we look at many groups caught at different moments. One particularly important feature of galaxy groups is dark matter. The visible galaxies are only part of the total mass. If astronomers measure how quickly galaxies move within a group, they often find that the visible stars and gas cannot provide enough gravity to explain those motions. The galaxies should escape, yet they remain associated. Something unseen contributes additional mass. Again, dark matter provides the leading explanation. A galaxy group is thought to sit inside a much larger dark matter halo. Individual galaxies have their own halos, but on group scales those halos can be embedded within an even broader distribution of dark matter surrounding the whole system. This means that when two galaxies orbit within a group, they are not simply reacting to each other's visible stars. They are moving through a shared gravitational landscape dominated largely by something we cannot see directly. The same invisible framework that helped galaxies form continues organizing them on larger scales. One useful example beyond our immediate neighborhood is the M81 group. It contains the large spiral galaxy Messier 81, the starburst galaxy Messier 82, and several smaller companions. M81 and M82 have interacted gravitationally. Those interactions appear to have disturbed gas and contributed to intense star formation in M82. The two galaxies provide a clear example of how membership in a group can change the internal evolution of a galaxy. A galaxy does not need to merge completely with another to be affected. A relatively close gravitational encounter can be enough. The encounter can distort a disk. It can produce tidal arms. It can compress gas. It can trigger star formation. Material can be pulled from one galaxy and deposited into the space between them. A galaxy group is therefore not simply a container holding separate galaxies. The members influence one another. Another famous example is Stephan's quintet, a visually striking arrangement of galaxies discovered in the 19th century. The name suggests 5 galaxies physically interacting together, although one of the visible members is actually much closer to us and only happens to lie along the same line of sight. The remaining interacting galaxies show strong evidence of gravitational encounters, including distorted shapes, tidal features, and shock-heated gas. This is a useful reminder that apparent groups on the sky are not always genuine physical groups. Astronomers must measure distances and velocities. Galaxies that look close together from Earth may be separated by hundreds of millions of light-years. Once again, the sky gives us a 2-dimensional projection of a 3-dimensional universe, and leaves us to sort out the depth ourselves. When galaxies really do occupy the same group, interactions tend to occur more readily than they do in very large galaxy clusters. This may sound surprising. A cluster contains more galaxies, so you might expect more mergers. But the galaxies in rich clusters often move at very high speeds relative to one another. They can pass too quickly for gravity to bind them into a merger. In smaller groups, relative speeds are often lower. That gives galaxies more time to interact gravitationally during close encounters. As a result, groups can be important places for galaxy mergers. Over long periods, repeated mergers may reduce the number of separate large galaxies in a group. Several galaxies can combine into one dominant system. In an extreme case, nearly all the major galaxies may merge together, leaving one unusually bright elliptical galaxy surrounded by hot gas and a population of much smaller galaxies. Astronomers sometimes call such systems fossil groups. The name does not mean the galaxies have been turned to stone. It refers to the idea that the system preserves the aftermath of earlier merging. The large central galaxy is effectively the surviving record of several former major members. A fossil group can therefore look strangely empty around its brightest galaxy. The relatives have not gone on holiday. They have become part of the host. This process helps explain how very massive elliptical galaxies may grow. Galaxies can assemble through repeated mergers inside groups before those groups become part of still larger structures. That makes groups an important intermediate step in hierarchical cosmic growth. Small dark matter halos merge. Galaxies form inside them. Those galaxies gather into groups. Groups can later fall into galaxy clusters. The hierarchy keeps expanding, but before moving outward, there is more happening between the galaxies than the darkness in photographs might suggest. Intergalactic space within a group is not truly empty. It can contain diffuse gas. Some of this material is extremely hot and emits X-rays. In sufficiently massive groups, the gravitational potential is strong enough to hold gas that has been heated to millions of degrees. This hot intra-group medium can contain a significant amount of ordinary matter. That may sound odd. If the gas is so hot, why does it not simply fly away? The answer is gravity. The dark matter halo of the group creates a deep gravitational well. Gas falling into that well gains energy and can be heated through shocks and compression. The hotter the system, generally speaking, the more massive the gravitational environment required to confine it. In the largest galaxy clusters, this process becomes even more dramatic. There, the gas between galaxies can outweigh the stars in all the galaxies combined. Groups are a quieter version of that same idea. Astronomers study this hot gas using X-ray telescopes because ordinary visible light observations can miss it almost entirely. A group that looks like a few isolated galaxies in an optical image may reveal a broad cloud of hot gas when viewed in X-rays. This is another useful lesson in cosmic structure. What you see depends strongly on how you look. Visible light emphasizes stars. Radio observations can reveal neutral hydrogen. X-rays reveal hot plasma. Gravitational lensing can reveal mass whether or not that mass shines. Different observations build different maps of the same group. Put those maps together and the system becomes much more complete. Gravitational lensing is especially interesting. According to general relativity, mass bends space-time, and that bending changes the path of light. A sufficiently massive foreground object can distort or magnify the appearance of more distant galaxies behind it. In very massive galaxy clusters, this effect can produce dramatic arcs and multiple images. In galaxy groups, the lensing is usually weaker, but it can still help astronomers estimate how mass is distributed. Since dark matter does not emit light, lensing provides a way to map its gravitational influence without needing to see it directly. The universe has kindly supplied an invisible substance, and then required us to study it by watching background galaxies become slightly distorted. Astronomers have accepted the challenge. Dark matter also influences the fate of satellite galaxies. A dwarf galaxy orbiting a larger member can be stripped by tidal forces. Its outer stars may be removed first. Over time, the satellite can lose enough material to become severely distorted or dissolve. Gas can be lost as well. Some dwarf galaxies near the Milky Way contain very little gas and little ongoing star formation. More distant dwarfs can sometimes remain more gas-rich. Environment appears to play an important role. A satellite moving through a larger galaxy's hot gaseous halo may experience ram pressure stripping. This happens when the gas inside the moving galaxy encounters the surrounding medium. The galaxy stars pass through relatively unaffected because stars are tiny and widely separated. Gas behaves differently. It feels pressure. If the pressure is strong enough, gas can be pushed out of the galaxy. Without cold gas, future star formation declines. The galaxy becomes quieter and redder as its young stars age. This effect becomes much stronger in massive clusters, but smaller scale versions can operate in groups as well. Tidal forces create another route for removing material. Gravity from a large galaxy is stronger on the nearer side of a small satellite than on the farther side. That difference can stretch the satellite. Stars are pulled into streams, gas is disturbed. Repeated passages can gradually dismantle the smaller system. The local group contains multiple examples where these processes can be studied close enough for astronomers to examine individual stars. That proximity is incredibly useful. In distant galaxies, an entire stellar population may appear as one unresolved patch of light. In nearby dwarf galaxies, telescopes can identify individual stars, estimate their ages, measure their chemical compositions, and reconstruct detailed star formation histories. The local group therefore acts as a laboratory for understanding galaxy evolution. We cannot conduct controlled experiments on galaxies. There is no spare Milky Way available in a nearby room where we can increase the dark matter by 10% and see what happens. Astronomy relies on observation. Nearby systems provide the detail. Distant systems provide the variety. Computer simulations help connect the two. Modern simulations of galaxy formation begin with early density variations and follow the effects of gravity, dark matter, gas dynamics, star formation, supernovae, black holes, and cosmic expansion. As the simulation evolves, dark matter forms a network of halos and filaments. Gas falls into those halos, galaxies appear, small systems merge, groups emerge. Some groups later combine into clusters. When astronomers compare these simulated universes with real observations, they can test whether our physical models reproduce the kinds of structures we actually see. Not perfectly. Galaxies are difficult, gas is difficult, star formation is difficult. Black hole feedback is especially fond of making computer models complicated. But simulations have become remarkably successful at reproducing many broad features of cosmic structure. One of those features is the way galaxy groups connect to the larger environment. A group does not float in complete isolation. Groups often lie along filaments of the cosmic web. Material flows along those filaments. Small galaxies can fall into groups. Groups can move toward larger concentrations. The local group itself exists within a wider region containing many nearby galaxy groups and clusters. Its motion is influenced by mass distributed beyond its immediate membership. This is where older terminology can become confusing. You may have heard that the local group belongs to the Virgo Supercluster. You may also have heard the name Laniakea. These names describe larger scale arrangements in somewhat different ways. The farther outward we move, the less simple the idea of a sharply bounded gravitational structure becomes. At the scale of a small galaxy group, membership can often be connected reasonably clearly to gravity. At supercluster scales, cosmic expansion and complex flows make the boundaries less tidy. For now, the important point is that the local group is one small concentration within a much larger landscape. Nearby is the Virgo cluster, a far richer gathering of galaxies located tens of millions of light-years away. Its gravitational influence helps shape motions throughout our broader cosmic neighborhood. The difference between the local group and a system like Virgo is substantial. The local group contains a few large galaxies and many dwarfs. Virgo contains well over 1,000 known galaxies and much more total mass. Hot gas fills its interior. Galaxies move through it at high speeds. A massive elliptical galaxy sits near its central region. The environment is much denser and more active. This illustrates the gradual transition between groups and clusters. Nature does not provide a bright line at exactly 50 galaxies and say everything below is a group and everything above is a cluster. The distinction often depends on richness, mass, size, dynamical properties, and observational convention. Poor clusters and rich groups can overlap in some characteristics. The categories are useful, but cosmic structure remains a continuum. A small group might contain only a handful of luminous galaxies. A rich group may contain dozens. Keep increasing the mass and population, and eventually the system begins behaving like the enormous environments astronomers call galaxy clusters. The hot gas becomes more prominent, velocity dispersions increase, gravitational lensing becomes stronger, environmental effects on galaxies become more severe. Hundreds or thousands of galaxies can occupy the same broad gravitational well. At that point, the scale changes once more. A single galaxy, even one as large as the Milky Way, becomes only one moving member of a much greater system. Imagine shrinking every galaxy in the local group until each one became a small glowing lantern. You might have a modest collection scattered across a dark field. Now imagine adding hundreds more lanterns, surrounding them with a cloud of gas heated to tens of millions of degrees, embedding the whole system in an enormous dark matter halo, and allowing every member to move under the combined gravity of the entire structure. That begins to resemble a galaxy cluster. A galaxy cluster is where the universe begins to feel genuinely crowded. Not crowded in the everyday sense, of course. There is still an absurd amount of empty space between one galaxy and the next. You could travel for millions of years at ordinary spacecraft speeds and never accidentally bump into one. But compared with a small galaxy group, a rich cluster is a major concentration of matter. Hundreds or even thousands of galaxies can occupy the same enormous gravitational environment. Some are spirals, some are ellipticals, some are small dwarf galaxies, some are distorted by interactions. Many are moving at hundreds or even more than 1,000 kilometers per second, relative to the cluster as a whole, and all of them are embedded inside something much larger than the visible collection of stars. A galaxy cluster contains three major components. The galaxies themselves are the easiest part to see. Then there is an enormous reservoir of extremely hot gas filling the space between them. And surrounding everything is a much larger distribution of dark matter that provides most of the cluster's mass. If you looked at a cluster only in visible light, you would naturally assume the galaxies were the main event. They are bright, they are large, they photograph well. Astronomically speaking, they have excellent public relations. But when scientists measure the total mass of a cluster, the stars in those galaxies account for only a relatively small fraction. A larger amount of ordinary matter exists in the hot gas between the galaxies. Most of the mass, however, appears to be dark matter, so the great cities of galaxies are built mostly from material we cannot see directly. The illuminated residents are only tracing the structure. That hot gas is called the intracluster medium. The name is not especially imaginative, but it does have the advantage of telling you exactly where the gas is. It fills the space between cluster galaxies and can reach temperatures of tens of millions of degrees. At temperatures like that, atoms are stripped of many or all of their electrons, producing an ionized plasma. This gas is so hot that it emits strongly at X-ray wavelengths. A visible light image of a galaxy cluster might show hundreds of separate galaxies against black space. An X-ray image can reveal a broad glowing cloud filling much of the same region. Suddenly, the supposedly empty gaps between the galaxies are not empty at all. They contain enormous amounts of matter. The gas became hot partly because of gravity. As material fell into the cluster's deep gravitational potential, it accelerated. Gas streams collided, shock waves formed, motion was converted into heat. The result is a vast atmosphere surrounding the entire cluster. It is very different from an atmosphere around a planet. There is no clear surface below it, no weather forecast, no sensible place to bring an umbrella, but physically, the idea of a hot diffuse medium held by gravity is useful, and because the temperature of the gas depends on the depth of the gravitational well, X-ray observations can help astronomers estimate how massive a cluster is. There are other methods as well. One is to measure the motions of the galaxies. If galaxies are orbiting within a cluster at very high speeds, there must be enough mass to keep them gravitationally bound. This became historically important in the 1930s when astronomer Fritz Zwicky studied the Coma cluster. He measured the velocities of its galaxies and found something troubling. They were moving too fast. If the cluster contained only the mass visible in stars, it should have flown apart. The galaxies appeared to require much more gravity than the luminous matter could provide. Zwicky proposed the presence of unseen matter. This was an early version of what we now call the dark matter problem. At the time, the idea did not immediately transform astronomy. Decades passed before additional evidence from galaxies, clusters, gravitational lensing, and cosmology made dark matter central to our picture of the universe. Still, the basic puzzle was already sitting there in the Coma cluster. The galaxies were behaving as if something invisible was holding them together. Coma remains one of the best-known rich clusters. It contains more than 1,000 large galaxies and many smaller ones. Unlike the local group, where spirals such as the Milky Way and Andromeda dominate our attention, the central parts of rich clusters often contain many elliptical and lenticular galaxies. This difference is not accidental. Environment changes galaxies. A spiral galaxy entering a cluster encounters conditions very different from those in a relatively quiet group. It begins moving through hot intracluster gas. That movement can strip away its own colder gas. This is ram pressure stripping, which we encountered on a smaller scale in galaxy groups. In a massive cluster, the process can be far stronger. Think of a galaxy moving through the intracluster medium like someone cycling quickly through heavy rain. The stars barely notice. They're individual compact objects separated by enormous distances. The galaxy's gas, however, feels pressure from the surrounding medium. If the pressure becomes strong enough, the gas can be pushed out of the galaxy. Sometimes it forms a long trailing tail. Astronomers have observed galaxies with streams of stripped gas extending behind them, producing shapes that have earned the nickname jellyfish galaxies. Because apparently the universe has not finished naming astronomical objects after animals. These galaxies can be spectacular. Bright regions of new star formation may appear in their stripped tails. The pressure that removes gas can also compress some of it temporarily, triggering star formation before the material is finally lost. Eventually, however, removing cold gas deprives the galaxy of the raw material needed to make new stars. Star formation declines. The galaxy becomes dominated by older stellar populations. Its appearance changes. This is one reason dense clusters contain so many galaxies with little active star formation. Gravity contributes additional forms of harassment, and galaxy harassment is, rather wonderfully, an actual term astronomers use. A galaxy moving through a crowded cluster experiences repeated high-speed gravitational encounters with other galaxies. These encounters may be too fast for full mergers, but they can still disturb stellar disks, alter shapes, and remove material. The overall gravitational field of the cluster also exerts tidal forces. Smaller galaxies are especially vulnerable. Their outer stars can be stripped away. Their structures can be reshaped. A galaxy that entered the cluster as a neat spiral may look very different after billions of years in that environment. Cluster membership comes with consequences. It is rather like moving into an extremely busy city and discovering that the traffic has opinions about your internal structure. Not every part of a cluster is equally busy. The central region is usually the densest. Near the centre, astronomers often find one or more enormous elliptical galaxies. These are sometimes called brightest cluster galaxies, or BCGs. They are among the most luminous and massive galaxies known. Some extend far beyond ordinary galactic scales and possess huge envelopes of stars. Their growth is linked to the cluster environment. Over long periods, smaller galaxies can lose orbital energy and move inward. Mergers add stars to the central galaxy. Material stripped from other galaxies contributes to a faint diffuse glow spread through the cluster. This light is called intracluster light. It comes from stars that no longer clearly belong to any one galaxy. They orbit within the cluster's gravitational field instead. That is a rather strange fate for a star. Born in a galaxy, carried around for billions of years, then stripped away by gravitational interactions and left travelling through the space between galaxies. If a planet orbited such a star, its night sky would be extraordinary. The nearest large galaxies might appear as extended patches rather than distant smudges. Yet the star itself would no longer be clearly attached to any one of them, a true intergalactic resident, although still very much inside the cluster. The centre of a cluster can also contain enormous quantities of hot gas. In some systems, the gas is densest near the core. Because denser gas radiates energy more effectively, astronomers once expected large amounts of this material to cool rapidly and flow toward the centre. These systems became known as cooling flow clusters. But observations revealed that the gas often does not cool as quickly as simple models predicted. Something appears to reheat it. One important source is the central supermassive black hole. A massive galaxy near the centre may contain an active galactic nucleus. As gas falls toward the black hole, enormous amounts of energy can be released. Jets blast outward. Those jets inflate huge bubbles or cavities in the surrounding X-ray emitting gas. The energy can stir and heat the intracluster medium, preventing much of it from cooling. This creates another feedback loop. The cluster's gas begins cooling. Some material feeds the central black hole. The black hole becomes more active. Energy is released back into the surrounding gas. Cooling slows. The black hole has effectively become part of the cluster's heating system. A heating system with relativistic jets and a supermassive black hole is perhaps slightly excessive for the average home, but it appears to work. One famous example is the Perseus cluster. Its central galaxy, NGC 1275, hosts an active black hole that produces jets and large cavities in the surrounding hot gas. X-ray observations reveal ripples and structures throughout the intracluster medium. Researchers have even interpreted some of these pressure waves as extremely low-frequency sound waves moving through the gas. You could not hear them with human ears. Their frequencies are far below our hearing range. Unfortunately, there is no practical way to stand inside the Perseus cluster with a microphone. But physically, pressure waves are travelling through the plasma. So while we often call space silent, certain environments contain media capable of carrying waves that are, in a technical sense, sound. They simply operate on scales and frequencies that make ordinary conversation rather difficult. Galaxy clusters are also among the most useful gravitational lenses in the universe. Their enormous mass bends space-time strongly enough to alter the paths of light from more distant galaxies behind them. This can stretch background galaxies into long arcs. Sometimes multiple images of the same distant galaxy appear around the cluster. In especially favourable alignments, lensing can magnify objects that would otherwise be too faint to observe. The cluster becomes a natural telescope, a very heavy, invisible, slightly distorted telescope. Astronomers use these effects for two purposes at once. First, lensing reveals distant galaxies. Second, the amount of distortion tells us about the mass of the cluster producing it. Because gravity responds to all mass, not just luminous matter, lensing can map dark matter. This becomes particularly striking in clusters that are colliding with other clusters. Yes, galaxy clusters can collide too. At this scale, entire collections of hundreds or thousands of galaxies can approach one another, merge, and become a larger system. The process takes billions of years. During a cluster collision, the individual galaxies mostly pass through with relatively few direct interactions. Again, stars and galaxies are small compared with the enormous distances separating them. The hot gas behaves differently. Gas from one cluster crashes into gas from the other. It slows. It heats. Shock waves spread through the plasma. Dark matter, meanwhile, appears to pass through much more freely because it does not interact strongly through ordinary electromagnetic forces. One of the most famous examples is the Bullet cluster. This system consists of two galaxy clusters that have passed through one another. Observations show that the hot X-ray emitting gas is separated from much of the mass inferred through gravitational lensing. The ordinary gas collided and slowed. The dominant mass component continued onward with the galaxies. This separation provides strong evidence that most of the mass is in a component behaving differently from ordinary matter. Dark matter is not merely an adjustment added to equations, because galaxy rotation curves look inconvenient. It appears on cluster scales in multiple independent ways. The Bullet cluster is visually dramatic because those components become physically separated enough to map. Other colliding clusters provide similar laboratories. They let astronomers examine shock waves, dark matter behavior, magnetic fields, particle acceleration, and the physics of extremely hot plasma. Cluster mergers are among the most energetic events in the universe since the Big Bang. Unlike supernovae, they do not release all that energy in a brief flash. The process unfolds across millions of light years and over immense timescales. Two enormous gravitational systems interpenetrate. Gas heats to extraordinary temperatures. Galaxies are thrown into new orbits. The dark matter distributions combine. Eventually, the disturbed system relaxes into a new, larger cluster. That word, relaxes, is doing considerable work. A galaxy cluster can take billions of years to settle after a major merger. Astronomers classify clusters partly by whether they appear dynamically relaxed or disturbed. A relaxed cluster tends to have a more regular shape, with hot gas distributed smoothly around the center. A merging cluster may look lopsided or contain multiple concentrations. Shock fronts, displaced gas, and irregular mass distributions reveal ongoing activity. Because clusters form through repeated mergers and accretion, they preserve a record of cosmic structure formation. Small systems fall inward, groups are absorbed, matter arrives along filaments, clusters grow. This process continues today. They are not finished objects. A large cluster can still gain mass from surrounding groups and galaxies. The outskirts are especially interesting because this is where material enters. Galaxies falling into a cluster for the first time may still contain significant gas and active star formation. As they travel inward, the environment begins changing them. Astronomers can compare galaxies at different distances from the cluster center and look for evidence of this transformation. The outer regions may contain more blue star-forming galaxies. The core may contain more red, passive ellipticals. This relationship between environment and galaxy type was recognized decades ago and remains an important clue to how galaxies evolve. But environment is not the only factor. A galaxy's mass, merger history, gas supply, and internal black hole activity all matter too. Separating these influences is difficult. If a galaxy has stopped forming stars, was the cluster responsible? Did a black hole remove or heat the gas? Was the fuel exhausted before the galaxy arrived? Did an earlier group environment already begin the process? Astronomy likes questions with multiple acceptable suspects. Groups falling into clusters provide one possible answer to the last of those questions. A galaxy may begin changing before it ever enters the main cluster. This is sometimes called pre-processing. Imagine a small group approaching a massive cluster. Its galaxies have already interacted with one another. Some have merged, some have lost gas. Then the entire group falls into the cluster. The cluster is not receiving pristine galaxies. It is receiving a family that has already spent billions of years interfering with itself. The larger environment continues the work. This makes galaxy clusters the result of nested assembly. Individual galaxies contain stars. Galaxies form groups. Groups fall into clusters. Clusters themselves grow by absorbing smaller clusters and surrounding material. At each scale, gravity gathers what existed at the scale below. The total masses involved are astonishing. A rich galaxy cluster can contain hundreds of trillions, or even more than a quadrillion times the mass of the Sun. Most of that is dark matter. The hot gas contributes another substantial fraction. All those brilliant galaxies contribute surprisingly little by comparison. Clusters can extend across several million light-years, with their gravitational influence reaching farther into surrounding space. And yet even objects this large are not randomly distributed through the universe. This is where the idea of a cosmic city becomes useful. Cities are not scattered evenly across a continent. They appear where geography, resources, transportation, and history allow them to grow. Galaxy clusters also occupy preferred locations. They develop where the underlying distribution of matter is especially dense. On the largest maps of the universe, clusters often sit where long filaments of galaxies intersect. They are knots in a network. Matter flows toward those knots over cosmic time. Groups enter along the surrounding filaments. Galaxies fall inward. The cluster grows at the meeting point. This network was seeded by tiny density variations in the early universe. Gravity amplified them. Dark matter collected first into small halos and then progressively larger structures. Ordinary gas followed. Galaxies formed. Groups appeared. Clusters grew where the concentration became greatest. So when we look at a galaxy cluster, we are seeing more than a gathering of galaxies. We are seeing the visible result of billions of years of gravitational construction. The cluster marks one of the densest regions in the cosmic landscape. But even a cluster does not define the largest meaningful concentration of galaxies. Zoom farther out and several clusters may appear to belong to the same broad region. They can be connected by chains of galaxies and groups. Their motions can reflect larger patterns of matter around them. Historically, astronomers began calling these enormous associations superclusters. The term sounds straightforward. A galaxy cluster can be treated as a single gravitational system. Its galaxies, hot gas and dark matter, occupy a shared potential well. Move to supercluster scales, however, and the idea becomes less tidy. A supercluster is not simply an oversized galaxy cluster. That distinction matters. Galaxy clusters are generally gravitationally bound structures. Their members can remain together despite the overall expansion of the universe because local gravity is strong enough to dominate. Superclusters are much larger. They can contain many galaxy groups, rich clusters, smaller clusters, and enormous numbers of individual galaxies spread across tens or hundreds of millions of light years. At those distances, cosmic expansion becomes important. Some parts of a supercluster may be gravitationally connected strongly enough to move toward one another. Other parts may never collapse into a single object. So when astronomers use the word supercluster, they're often identifying a large concentration in the distribution of galaxies, rather than one enormous object with a simple edge. The name sounds more decisive than the structure itself. Astronomy occasionally does this. We create a useful label, put it on something vast and complicated, and only afterward admit that the boundaries are a little fuzzy. Our own cosmic region provides a good example. The local group, containing the Milky Way, Andromeda, Triangulum, and many dwarf galaxies, lies near the outskirts of a much larger concentration historically called the Virgo Supercluster. The Virgo cluster is one of the dominant nearby galaxy clusters and sits roughly 50 to 60 million light-years from us. Around it are many smaller groups and concentrations of galaxies. For decades, this broader region was a convenient way to describe our larger galactic neighbourhood. Then astronomers began examining galaxy motions in greater detail. Instead of asking only where galaxies were located, they looked at how galaxies were moving. This revealed a larger pattern. The Milky Way and many surrounding galaxies appear to participate in a broad flow toward a region of greater mass. By mapping these motions, researchers identified an even larger structure known as Laniakea. The name comes from Hawaiian and is often translated as something like immense heaven. It is an appropriate name for a region containing on the order of tens of thousands of large galaxies and extending across hundreds of millions of light-years. But even Laniakea is not a solid cosmic continent in the way Australia is a continent. There is no coastline, no cliff, no sign announcing that you are now leaving Laniakea and should adjust your clocks accordingly. Its boundary is defined using the motions of galaxies. Within a particular region, galaxies tend to flow toward a shared gravitational basin. Outside that boundary, their motions are directed toward other large concentrations. This gives the supercluster a kind of watershed. On Earth, water falling on opposite sides of a mountain ridge may eventually flow into different rivers. On cosmic scales, galaxies in neighbouring regions can respond to different large-scale gravitational attractors. The analogy is not perfect because galaxies are not droplets sliding downhill through fixed terrain. The terrain itself is part of the evolving distribution of matter. Still, it is a useful way to understand why astronomers can define very large regions without requiring a hard physical edge. Inside Laniakea, one important gravitational destination lies in the direction of what astronomers call the Great Attractor. That name sounds as though the universe has hired a particularly confident marketing department. The Great Attractor is not one giant object. It is a region where a substantial concentration of mass affects the motion of nearby galaxies, including our own. Observing it has historically been difficult because it lies close to the plane of the Milky Way from our point of view. The disk of our galaxy contains stars, gas and dust that obscure distant objects behind it. Astronomers call this obscured region the zone of avoidance. Again, an excellent name. It sounds like somewhere a sensible traveller should not stop after dark. In reality, it simply means that visible light surveys struggle to see distant galaxies through the crowded galactic plane. Radio, infrared, X-ray and other observations can penetrate some of that obscuration and reveal more of what lies beyond. Those observations have shown that the Great Attractor is part of an even richer large-scale environment, involving several clusters and surrounding structures. One of the major concentrations in that direction is the Norma cluster. Farther beyond lies the enormous Shapley Supercluster, another very rich concentration of galaxy clusters. This immediately gives us a sense of the problem with treating a supercluster as an isolated object. Zoom out far enough, and the apparent structure becomes connected to other large concentrations. One supercluster can sit near another. Filaments extend between them. Clusters form along those filaments. Broad sheets of galaxies connect regions that initially looked separate. The farther we zoom out, the more the boundaries begin to resemble lines drawn for convenience across a continuous pattern. This does not mean superclusters are imaginary. The concentrations are real. Galaxies are genuinely distributed unevenly. There are regions containing far more matter than average. But the question of exactly where one supercluster ends and another begins depends partly on how we define the structure. Different surveys and methods can produce different boundaries. One approach looks at galaxy density, another studies motions, another identifies chains of connected clusters. The resulting maps can describe the same universe in slightly different ways. It is a bit like looking at a physical map, a political map, and a population map of the same country. The mountains are real, The cities are real, the borders are useful. But each map emphasizes a different kind of structure. Superclusters were first recognized when astronomers began obtaining large enough samples of galaxy positions to notice that clusters themselves were clustered. This sounds almost comically repetitive. Galaxies gather into clusters, then clusters gather into larger concentrations. At some point you begin to suspect gravity has only one organizing idea, and is extremely committed to it. Early galaxy surveys showed that galaxies were not spread randomly across space. As observations improved, large concentrations emerged. The Coma cluster, for example, is part of a broader region associated with the Coma Supercluster. Other famous supercluster regions include Perseus Pisces, Shapley, and Hercules. Each contains multiple groups and clusters distributed across huge distances. The Perseus Pisces supercluster is particularly striking because it forms a long chain-like concentration of galaxies stretching across a significant part of the nearby universe. Rather than looking like one round blob, it resembles an extended ridge. That shape is an important clue. If superclusters were simply the next level in a sequence of increasingly large spherical structures, the story would be easy. A star is inside a galaxy. A galaxy is inside a group. A group is inside a cluster. A cluster is inside a supercluster. Then perhaps the supercluster would be inside something still larger. But the large-scale universe does not organize itself as a set of perfectly nested spheres. Instead, matter develops into elongated filaments, broad sheets, dense knots, and underdense regions. Superclusters are often portions of that network. They are not necessarily a separate final tier. This is why the analogy of continents works only up to a point. A continent on Earth is a reasonably coherent mass separated by ocean. A cosmic supercluster may be part of one continuous chain of matter extending into neighbouring large-scale structures. The separation is less obvious. What creates these enormous concentrations comes back to the same early density variations we have followed since the beginning of our journey. The young universe was nearly uniform, but not perfectly. Some regions contained slightly more matter than others. Dark matter began collecting around those denser regions. Small halos formed first. Halos merged. Galaxies developed within them. Groups and clusters assembled. Over billions of years, the largest initial overdensities grew into the regions we now recognize as major supercluster complexes. Gravity amplified the original differences. At the same time, the universe expanded. Those two processes competed. Gravity tried to pull matter together. Expansion increased distances between regions that were not strongly bound. At smaller scales, gravity generally wins. Earth remains attached to the Sun. The solar system does not expand with the universe. The Milky Way remains a galaxy. The local group is gravitationally bound strongly enough that Andromeda approaches us, rather than receding with cosmic expansion. Galaxy clusters can remain bound as well. At supercluster scales, the balance becomes different. The entire structure may not overcome the accelerating expansion of the universe. This means that in the extremely distant future, parts of what we currently call the same supercluster could become causally separated. Galaxies not gravitationally bound to our local region will continue receding. Over immense spans of time, cosmic expansion can carry them so far away that their light becomes increasingly redshifted and eventually effectively inaccessible. The present universe therefore gives us a special opportunity. We can see a wide network of surrounding structures that distant future observers may not be able to detect. A civilization living many tens or hundreds of billions of years from now, assuming stars and suitable environments still exist, might see a much emptier cosmos. Its local gravitationally bound group could remain. But distant galaxies would have been carried beyond visibility by accelerated expansion. Such observers might have far less evidence for the larger universe than we do. For now, however, our telescopes can map enormous volumes. and what they reveal makes the scale of superclusters especially striking. Imagine taking the Milky Way and reducing it to a dot, then do the same to Andromeda and every other galaxy in the local group. The entire group becomes one tiny mark. Move outward. The Virgo cluster becomes another mark. Other nearby groups and clusters appear, then continue until hundreds and thousands of these marks fill the map. At supercluster scale, individual galaxies disappear from practical consideration. Even clusters become points. The structure is defined by how those points are distributed. Dense regions stand out. Long chains appear. Empty-looking gaps widen between them. A map like this can be built from galaxy redshift surveys. Astronomers measure the light from large numbers of galaxies and determine how much their spectral features have been shifted toward longer wavelengths. Because the universe is expanding, redshift generally increases with distance, although local motions add complications. By combining angular positions on the sky with estimated distances, astronomers can create three-dimensional maps of galaxy distribution. Some of the early large redshift surveys revealed patterns that surprised researchers. Galaxies appeared concentrated along broad surfaces surrounding enormous empty regions. A slice through the universe looked somewhat like foam. Matter gathered along the boundaries. Large, low-density spaces occupied the interiors. Later surveys expanded this picture enormously. Projects mapping hundreds of thousands and then millions of galaxies showed that the universe contains a complex network of structure on scales, far beyond individual clusters. Some large concentrations became famous in their own right. The Sloan Great Wall, for example, is an enormous arrangement of galaxies stretching across more than 1 billion light-years, depending on exactly how the structure is defined. Another structure known as the Hercules Corona Borealis Great Wall has been proposed on even larger scales based on the distribution of gamma-ray bursts, although its nature and significance have been debated. At these scales, astronomers have to be careful. A structure can appear enormous partly because of the way it is identified. If you connect enough neighbouring concentrations using a particular mathematical criterion, you can sometimes create something that looks like one single structure, even when it may be better understood as several connected regions. This is not unique to cosmology. Imagine looking down at nighttime lights across Europe. Depending on how generously you define continuous illumination, you might connect towns and cities into one enormous glowing network. That does not necessarily mean the entire network is one city. Large-scale cosmic structures raise similar classification problems. The question becomes not only, is there matter here, but does this concentration behave as one physical object? For superclusters, the answer is often only partly. Some central portions may eventually collapse or remain bound. More distant sections may expand away. This is one reason modern cosmologists often emphasize the cosmic web, rather than treating superclusters as the largest discrete objects. Superclusters are important features within the web. They mark especially rich concentrations. But the web is the broader pattern. Still, these vast regions tell us a great deal about cosmology. Their abundance, sizes, and distribution depend on the properties of the universe. Change the amount of dark matter, and structure grows differently. Change the initial spectrum of density variations, and the pattern changes. Change the behavior of dark energy, and the future growth of a large-scale structure changes. Superclusters therefore help connect observations of galaxies to questions about the universe as a whole. They are not merely impressive addresses, they are evidence. Astronomers can compare the observed distribution of large structures with predictions from cosmological simulations. In those simulations, researchers begin with conditions resembling the early universe. Matter is distributed almost evenly, with tiny fluctuations drawn from measurements and cosmological theory. The simulation expands. Gravity amplifies the dense regions. Dark matter develops into filaments and halos. Galaxies populate those structures. Clusters form at intersections. Large concentrations emerge. When the simulated universe begins resembling the observed one statistically, scientists gain confidence that the underlying model captures important pieces of reality. The match does not require every simulated supercluster to resemble Laniakea exactly. Cosmology is interested in statistical patterns. How many structures of a certain mass appear? How strongly do galaxies cluster at different scales? How large are voids? How thick are filaments? How rapidly does structure grow over time? These measurements let astronomers test ideas about dark matter, dark energy, gravity, and the history of cosmic expansion. The superclusters themselves are therefore part of a much larger experiment, one in which the laboratory is the observable universe. There is another interesting consequence of viewing superclusters in this way. Their shapes tell us something about how matter moves. The universe does not generally funnel material straight into one central point from all directions. Matter tends to collapse first along one dimension, creating sheets, then along another, producing filaments. Finally, dense knots form where those filaments meet. This is a simplified picture, but it explains why large-scale structure naturally becomes web-like, rather than forming a uniform collection of isolated balls. Dark matter flows along the underlying gravitational landscape. Gas follows. Galaxies develop within the denser regions. Clusters grow at the intersections. Superclusters trace the richest portions of those interconnected patterns. Once you see the universe this way, a cluster is no longer just a city. It is a city sitting at a crossroads. The roads are filaments. Smaller groups travel along them. Matter continues falling inward. Voids lie between the roots. The cosmic map starts to resemble transportation infrastructure, although the traffic moves mostly because space-time has provided gravitational directions, rather than because anyone has painted arrows on the road. Our own large-scale neighbourhood participates in this flow. The local group has a motion relative to the overall expansion of the universe. Nearby groups have their own peculiar velocities, meaning motions in addition to the general Hubble expansion. By studying these velocities, astronomers infer where mass concentrations lie. The Great Attractor was identified partly through this kind of work. But as surveys improved, it became clear that the gravitational situation extended farther than one local concentration. The Shapley region contributes to the broader motion as well. This is another reminder that there is rarely a single object responsible for large-scale movement. Gravity is cumulative. Every concentration contributes. Nearby mass usually has a stronger effect. Very massive distant structures can still matter. The final motion of a galaxy reflects the combined gravitational field around it. Scale makes simple explanations progressively harder, and yet the overall pattern becomes visually clearer. Matter is not randomly sprinkled. It forms connected regions. The empty spaces between them are just as important as the concentrations themselves. A supercluster is noticeable partly because neighbouring regions contain less matter. Without underdense surroundings, an overdense region would not stand out. This introduces a slightly surprising idea. To understand the bigger structures, we have to study the empty parts too. Cosmic voids can span tens or even hundreds of millions of light years. They contain galaxies, but far fewer than average. As matter is gravitationally drawn toward denser regions, voids become increasingly empty relative to their surroundings. Their interiors expand effectively faster than dense regions, because there is less gravity slowing that local expansion. Over time, voids grow and merge. Their boundaries become lined with sheets, filaments, groups, and clusters. The superclusters we identify are therefore part of a pattern shaped as much by evacuation as by accumulation. Matter moves away from low-density regions and toward higher-density ones, not because the voids repel it in the ordinary sense, but because the gravitational pull is stronger toward the denser surroundings. Imagine raisins embedded in rising bread dough. If the raisins also happen to be moving toward other raisins because of gravity, the dough were expanding. The bakery were 13 billion years old, and someone had removed most of the useful parts of the analogy. Cosmology is hard on kitchen comparisons. Once filaments, walls, and voids come into view, the universe stops resembling a collection of separate cosmic objects and begins looking like one enormous connected structure. Galaxies are no longer the main shapes on the map. They become markers. Each one helps reveal where matter has gathered and where it has not. If we could remove the individual stars from our attention, blur entire galaxies into tiny points, and map millions of those points across an enormous volume of space, a pattern would gradually appear. The galaxies would not form a uniform mist. They would collect along long strands. Those strands would intersect at dense knots. Broad sheets would connect some regions. Between them would lie enormous spaces containing comparatively few galaxies. The result is what astronomers call the cosmic web, and the filaments are its most obvious threads. Cosmic filaments are enormous elongated concentrations of matter, stretching between galaxy groups, clusters, and larger overdense regions. Some extend across tens or hundreds of millions of light years. They contain galaxies, dark matter, and gas, although the majority of their mass is not visible in an ordinary telescope image. A filament is not a glowing cable hanging through empty space. It has no solid surface. There is no point where you would cross a sharp boundary and hear a small announcement saying that you've entered one. Instead, it is a region where the density of matter is higher than the cosmic average, and where that matter has become organized into a long connected structure. Galaxies trace the filament because they form more readily in these denser environments. Dark matter provides much of the underlying gravitational framework. Gas collects around the same structures. The visible galaxies are therefore something like streetlights along a road whose pavement is mostly invisible. You see the lamps and infer the route. This is why the cosmic web is sometimes described as the skeleton of the universe. The phrase is useful as long as we do not take it too literally. There are no cosmic bones, no enormous ribs, and thankfully no astronomer has yet had to explain where the universe keeps its knees. What the metaphor captures is the idea that large-scale matter is arranged along an underlying framework. Dark matter is central to that framework. In the early universe, tiny variations in density meant that some regions had slightly more matter than others. Dark matter began clustering gravitationally around those denser locations. Ordinary matter followed. As the universe expanded, gravity amplified the differences. Matter flowed toward overdense regions. Those regions became progressively more pronounced, but collapse did not occur equally in every direction. That detail helps explain the shapes we see now. Imagine a slightly denser region of matter that is not perfectly spherical. Gravity begins compressing it. The shortest dimension tends to collapse first. Matter may become flattened into a sheet. Then another dimension collapses, concentrating material into a filament. Finally, the densest regions along the filament can collapse into knots where groups and clusters form. This is a simplified description, but it gives us an intuitive picture of why the universe develops sheets, strands, and intersections instead of simply forming isolated round clumps everywhere. Gravity creates architecture, not intentionally, of course. Gravity does not own drafting equipment, but given billions of years and an uneven distribution of matter, it produces recognizable geometry. Clusters occupy some of the densest intersections. Several filaments can feed into one cluster. Galaxies and gas move along those filaments toward the central region. This is not merely a visual association on a map. The filaments act as channels through which matter continues arriving. A galaxy cluster can grow by absorbing groups and individual galaxies coming from the surrounding network. Gas flows inward as well. The cluster remains connected to its environment. If you imagine a large city supplied by several major highways, the comparison is not terrible. The cluster is the city. The filaments are the routes. Galaxy groups are the traffic. Dark matter built most of the road system, and no one appears to have installed service stations. The analogy becomes especially useful when astronomers study the orientations of galaxies and clusters. Because matter tends to flow along preferred directions, a cluster's shape can sometimes align with the filaments around it. Galaxies falling inward may also have motions that reflect those structures. Even the spins of galaxies can show statistical relationships with the surrounding cosmic web, although the details depend on galaxy mass and formation history. The environment leaves traces. A galaxy does not develop completely independently and then happen to land inside a filament. Its history is shaped by where it formed and how matter reached it. Filaments are therefore not merely connections between finished objects. They are environments where galaxies continue evolving. Their gas content is particularly important. Much of the ordinary matter expected from cosmological models is difficult to detect directly in nearby galaxies and clusters. Astronomers sometimes refer to a missing baryon problem. Baryons are the particles, mainly protons and neutrons, that make up ordinary matter. Measurements of the early universe tell us approximately how much ordinary matter should exist today. Yet when astronomers add up the readily visible stars and cold gas in galaxies, a substantial fraction is not immediately accounted for. One important place to look is the diffuse gas spread through filaments. This material can exist at temperatures between roughly hundreds of thousands and millions of degrees. It is often called the warm-hot intergalactic medium, a name that manages to be both accurate and slightly indecisive. Warm. Hot. Apparently the gas has chosen both. This material is difficult to observe because it is extremely diffuse. It does not glow brightly like a star. It may produce weak X-ray or ultraviolet signatures, and astronomers can also detect it when its atoms absorb particular wavelengths from the light of bright background objects. A quasar shining from far behind a filament can act like a flashlight. Its light passes through intergalactic gas. Atoms in that gas absorb specific wavelengths. By examining the resulting spectrum, astronomers can infer what material lies between us and the quasar. In this way, nearly invisible gas can reveal itself through what it removes from someone else's light. Astronomy often works by noticing that something is missing. Very polite detective work. Another technique uses fast radio bursts, brief flashes of radio emission arriving from distant galaxies. As their signals pass through diffuse ionized matter, different radio frequencies are delayed by slightly different amounts. Measuring this dispersion can tell astronomers how many free electrons the signal encountered along the way. That provides another way of studying otherwise difficult to see matter between galaxies. So the empty-looking filaments are not empty. They contain dark matter. They contain hot and warm gas. They contain galaxies. They contain groups. They can feed clusters. And they extend across distances so large that the individual galaxies along them become almost incidental. Some of the most spectacular filamentary structures have been mapped between neighbouring clusters. Astronomers have observed bridges of gas connecting massive systems, supporting the picture predicted by cosmological simulations. In other cases, the evidence comes from galaxy distributions and gravitational lensing. Weak gravitational lensing is particularly valuable. A filament's mass can slightly distort the shapes of much more distant galaxies behind it. The effect on any one background galaxy is tiny, but measure enough of them and a statistical pattern can emerge. That lets astronomers map mass that cannot be seen directly. Again, the visible galaxies are only part of the structure. The gravitational skeleton extends beyond them. Filaments can intersect with structures that astronomers describe as walls or sheets. A cosmic wall is a very broad, relatively flattened concentration of galaxies. Rather than forming a long, narrow strand, matter spreads across a large surface-like region. These structures can extend hundreds of millions of light-years. The word wall may suggest something dense and solid. It is nothing of the sort. If you entered one in a spacecraft, you would still find enormous distances between galaxies. You would not crash into a cosmic brick. You would probably not even notice the boundary without a very good map and several million years of travel data. The wall becomes obvious only when viewed on the right scale. This is a recurring feature of cosmic structure. The farther outward we move, the less useful direct human experience becomes. A planet can be imagined as a world, a star as a sun, a galaxy as an enormous collection of stars. But a wall containing thousands of galaxies spread across hundreds of millions of light years has no comfortable everyday equivalent. Maps help, computer visualizations help, food analogies begin to suffer. One of the historically important large structures is the CFA2 Great Wall, discovered through redshift surveys in the late 20th century. It appeared as an enormous concentration of galaxies extending across a significant part of the surveyed region. Later surveys found still larger features, including the Sloan Great Wall. The exact meaning of calling these structures single objects requires care. Large-scale galaxy distributions can contain connected filaments and clusters that statistical algorithms group together. Different definitions may produce different estimates of size, but the important physical point remains. Galaxies form broad, coherent patterns vastly larger than individual clusters. These walls often surround or border something almost opposite in character: voids. Cosmic voids are enormous underdense regions containing far fewer galaxies than average. Some span tens of millions of light years, others are considerably larger. At first, it is tempting to think of a void as a hole in the universe. It is not. Space continues through it. Dark matter is still present. Gas is still present. Galaxies can exist inside. There is simply much less matter than in the surrounding filaments and walls. If a rich cluster is a cosmic city centre, a void is more like an extremely rural region where your nearest neighbour may be unreasonably far away. Then move that neighbour another 10 million light-years down the road. Voids developed because matter was initially distributed unevenly. A slightly underdense region contains less gravitational pull than its denser surroundings. Over time, matter preferentially moves toward the denser regions. The underdense region becomes even emptier by comparison. As material flows outward toward walls and filaments, the void expands. This does not mean some mysterious force inside the void is actively pushing matter away. It is mostly a consequence of the surrounding gravitational landscape and cosmic expansion. Dense regions slow their local expansion through gravity. Underdense regions have less gravity resisting expansion. As a result, voids can grow. They can also merge. Smaller empty regions separated by relatively weak structures may gradually become part of larger voids. The large-scale universe evolves partly by building concentrations and partly by enlarging spaces between them. That is an important shift in perspective. Cosmic structure is not only the story of where matter goes, it is also the story of where matter leaves. The emptiness helps define the web. A filament looks like a filament because lower density regions surround it. A wall stands out because voids lie on either side. The map depends on contrast. Remove the voids, and the web loses much of its shape. Astronomers study voids for several reasons. One is that they provide unusual environments for galaxy evolution. A galaxy inside a deep void experiences fewer close encounters than a galaxy in a group or cluster. Mergers may be less frequent. The surrounding supply of gas can differ. Some void galaxies are small and actively forming stars. Others may lie along thin filaments threading through the void interior. Because the environment is less crowded, these galaxies offer a useful comparison with galaxies living in denser regions. If two galaxies have similar masses but very different surroundings, differences between them can reveal how strongly environment affects development. Voids are also valuable for cosmology. Their sizes, shapes, and distribution respond to the overall matter content of the universe and the way cosmic expansion changes with time. Because voids are dominated less strongly by dense, non-linear gravitational collapse than clusters are, they can provide complementary tests of cosmological models. They may help researchers investigate dark energy, gravity, and the growth of structure. So the emptiest places in the universe are scientifically full of information. That is a pleasingly inconvenient fact. The places with almost nothing in them can tell us a great deal. There is also an observational effect associated with large voids called the integrated Sachs-Wolf effect. Photons from the cosmic microwave background can pass through evolving gravitational potentials created by large-scale structures. If cosmic expansion is accelerating, those potentials change while the photons are crossing them. The photons can emerge with tiny changes in energy. By comparing maps of large-scale structures with the cosmic microwave background, astronomers can look for statistical traces of this effect. The signal is subtle. No one looks at a single void and sees the universe's expansion glowing around the edge. Cosmology often deals with tiny effects extracted from enormous datasets. Apparently, the largest structures require some of the smallest measurable differences. Voids can also distort the motions of surrounding galaxies. Galaxies near their edges tend to move toward neighbouring overdense regions. When astronomers map these motions, they can reconstruct parts of the underlying density field. The local group itself is influenced not only by large concentrations pulling on it, but also by the relative lack of matter in nearby underdense regions. A nearby cosmic void can contribute to our observed motion, in the sense that there is less gravitational pull from that direction. It is not pushing us. There is simply less pulling back. Imagine a tug of war where one side quietly goes home. The remaining team appears unusually persuasive. The same competition between overdense and underdense regions helps create the broad flows of galaxies across the cosmic web. Matter drains from voids. It collects along sheets. It moves into filaments. It gathers at nodes. This pattern appears vividly in computer simulations. When cosmologists simulate a large volume of the universe, dark matter particles initially form an almost smooth distribution. As time advances, tiny fluctuations grow. A delicate network appears, first faint, then increasingly sharp. Dense knots form. Thin strands connect them. Large dark regions open between the strands. By the present cosmic age, the simulation resembles the galaxy maps obtained from surveys. This agreement is one of the major successes of the modern cosmological model. The exact positions are not expected to match. A simulated cluster does not need to sit where the real Virgo cluster sits. What matters is that the statistical pattern resembles reality. The sizes of structures, the abundance of clusters, the distribution of voids, the way galaxies cluster at different distances, the overall geometry of the network. Much of that structure is governed by dark matter. Ordinary matter adds complexity because gas can heat, cool, form stars, explode in supernova, and interact electromagnetically. Dark matter mainly responds through gravity, making its large-scale behaviour somewhat simpler to model. This is why images from dark matter simulations often show the cosmic web so clearly. The invisible component forms a remarkably intricate framework. Galaxies develop preferentially within the dense parts of that framework. If we could somehow see dark matter directly, the universe might look very different. The bright points of galaxies would become embellishments sitting inside a far larger web. Around each galaxy would be an extended dark matter halo. Around groups and clusters would be larger halos. Filaments would connect them. Diffuse matter would stretch through regions that look black in ordinary photographs. The apparently empty universe would suddenly acquire structure almost everywhere. There is another detail worth remembering. The cosmic web is three-dimensional. Images often show it as a flat slice, because screens and pages are stubbornly two-dimensional. That can make filaments look like lines drawn across a sheet. In reality, they extend in every spatial direction. A cluster can connect to filaments arriving from above, below, ahead, behind, and directions for which our ordinary language becomes increasingly unhelpful. Walls are surfaces embedded within this three-dimensional arrangement. Voids are volumes surrounded by those surfaces and strands. The complete geometry is closer to a complicated foam or sponge than a flat spiderweb. Even those comparisons have limits. A sponge contains solid material with obvious holes. The cosmic web is mostly empty everywhere. Its dense regions would still qualify as excellent vacuums by terrestrial standards. Everything depends on scale and comparison. This can produce some surprising language. A galaxy cluster is one of the densest large structures in the universe, yet its galaxies remain separated by enormous distances. A cosmic filament is an overdensity, yet most of its volume contains almost nothing. A void is underdense, yet it can contain entire galaxies. The universe refuses to make adjectives easy. The boundaries are statistical. Dense means denser than average. Empty means emptier than average. Connected means linked through a continuous enhancement of matter, not physically joined like pieces of machinery. Once that becomes clear, the cosmic web stops, seeming like one enormous object, and starts looking more like a pattern created by the distribution of everything. There is no separate material called web. The web is the arrangement. Dark matter defines much of it. Gas fills parts of it. Galaxies illuminate it. Clusters mark its busiest intersections. Voids define its open spaces. Walls and sheets form broad boundaries. Filaments connect the concentrations. All of these structures are different aspects of the same gravitational history, and that history has been unfolding for almost the entire age of the universe. Early on, there were no mature galaxy clusters, no vast present-day filaments filled with developed galaxies, and no cosmic web as sharply defined as the one we observe now. The initial pattern existed only as tiny density differences. Gravity needed time, billions of years of it. The web gradually became more pronounced. Dense regions became denser. Voids became emptier. Clusters grew. Galaxies merged. Filaments continued feeding matter into nodes. The cosmic web is therefore still evolving. It is not a fossil frozen in place. Matter is still falling into clusters. Galaxies are still moving through filaments. Voids are still expanding. Large-scale structures are still changing, even though dark energy appears to be slowing the future growth of structure on the greatest scales by accelerating cosmic expansion. Eventually, regions not gravitationally bound will move farther apart. The cosmic web of the far future will not look exactly like the one we map today. The densest bound regions will persist. More distant structures will recede. The network visible to any one observer will gradually thin. But right now, we live at a time when enormous portions of it remain observable. From our position inside one small planetary system, inside one galaxy, inside one group, we can look outward and reconstruct a pattern extending across billions of light years. That is an extraordinary jump in scale. A human eye can look at a few faint galaxies, a telescope can detect millions, a survey can map their positions, a computer can reconstruct the three-dimensional distribution, and from those tiny points of light, the hidden skeleton emerges. When astronomers zoom out far enough, individual galaxies disappear into points. Zoom out farther, and even galaxy clusters stop looking like enormous systems. They become small, bright knots. Keep going, and the universe begins to reveal its largest recognizable pattern, the cosmic web. This is not one single object in the same sense as a star, a galaxy, or even a galaxy cluster. It is the large-scale arrangement of matter across the observable universe. Galaxies trace it. Clusters occupy some of its densest intersections. Filaments connect those dense regions. Walls spread across broad areas. Voids fill much of the space between them. Together, those structures form a network extending across hundreds of millions and billions of light years. And the remarkable part is that this enormous pattern began with differences so small that, in the early universe, they would have been difficult to notice at all. The young universe was extremely smooth. Matter and radiation were distributed almost evenly. Almost. That word does a great deal of work in cosmology. there were tiny variations in density. Some places contained a little more matter than average, others contained a little less. We can still see evidence of those early differences in the cosmic microwave background, the ancient radiation left from a time when the universe was only about 380,000 years old. Maps of that radiation show very small temperature variations across the sky. Those variations correspond partly to tiny differences in density. At the time, there were no galaxies like the Milky Way, no galaxy clusters, no enormous cosmic filaments filled with developed galaxies, no solar system, no Earth, and thankfully no alarm clocks. There were only the early ingredients and slight irregularities in how they were distributed. Gravity took it from there. A region containing slightly more matter had slightly stronger gravity. That region attracted additional matter. As it gained mass, its gravitational influence increased. More material arrived. The original difference became larger. Meanwhile, underdense regions lost matter relative to their surroundings and became emptier. Over billions of years, the small variations grew into the enormous contrast we see today. Dense regions became galaxies, groups, and clusters. Matter collected along filaments and sheets. Voids expanded between them. The cosmic web emerged. Dark matter was especially important in this process. Because dark matter does not interact with light in the ordinary way, it could begin forming gravitational structures without being affected by radiation in exactly the same manner as ordinary gas. Dark matter gathered into halos and larger connected structures. Ordinary matter then fell into those gravitational wells. Gas cooled in smaller halos. Stars formed, galaxies appeared. The luminous universe developed inside a framework that was already being shaped by invisible matter. This is why simulations of dark matter alone can produce such recognizable web-like patterns. They do not create every detail of real galaxies. For that, you need gas, star formation, supernova, black holes, magnetic fields, radiation, and an impressive amount of computing time. But the broad skeleton appears through gravity. In a typical cosmological simulation, the early distribution begins almost smooth. Then thin structures start appearing. Dense spots grow. Those spots become connected by strands. The strands sharpen. Empty regions widen. Eventually, the simulation fills with a network remarkably similar to the one revealed by galaxy surveys. This does not mean the simulated universe reproduces our exact cosmic neighbourhood. There is no requirement that a computer-generated Milky Way appears precisely where ours does. The important comparison is statistical. Do simulated universes contain similar numbers of galaxy clusters? Do their filaments have comparable properties? Are their voids distributed in similar ways? Do galaxies cluster at the same scales? Does structure grow at the observed rate? When the answer is broadly yes, that tells cosmologists that the model is capturing important features of how the real universe developed. The standard modern picture includes ordinary matter, dark energy, and an expanding universe that began in a much hotter, denser state. Within that framework, the cosmic web forms naturally. One useful way to understand the web is to imagine following a parcel of matter through cosmic time. Place it inside an underdense region. Gravity pulls more strongly toward neighbouring denser regions. The parcel begins moving outward from the void. Eventually it may join a broad sheet. From there, matter can flow toward a filament. The filament channels material toward a dense intersection. At that intersection sits a galaxy group or cluster. The movement is not as neat as water running through plumbing. There are no cosmic pipes, but simulations and observations both support the idea that matter flows preferentially through this hierarchy of structures. Voids lose matter, sheets collect it, filaments concentrate it further, nodes become the busiest regions. This process is still happening. Galaxy clusters are still accreting matter from their surroundings. Groups continue falling into clusters. Galaxies move along filaments. Gas enters large gravitational structures. The cosmic web is not a finished construction. It is the present form of a process that has been operating for billions of years. The rate of future growth, however, is changing. That is where dark energy enters the picture. The universe is expanding. On sufficiently large scales, distant galaxies tend to move away from one another as space expands. For much of cosmic history, gravity slowed that expansion. But observations show that the expansion is now accelerating. Dark energy is the name given to whatever is causing that accelerated expansion in our current models. We do not yet know its fundamental nature. It might be related to a cosmological constant, an energy associated with empty space. Other possibilities have been proposed. For our journey through cosmic structure, the important point is what accelerated expansion does to the web. Gravity can continue binding structures that are already sufficiently compact and dense. The solar system remains bound. The Milky Way remains bound. The local group remains bound. Galaxy clusters remain bound. But on much larger scales, regions that are not strongly gravitationally connected will move farther apart. That means the cosmic web does not grow forever in the same way. Large new gravitationally bound structures will not simply keep assembling without limit. The acceleration of expansion increasingly works against gravitational growth on the larger scales. Some structures we see connected today will become increasingly separated in the distant future. This gives the present cosmic web a temporary quality, not temporary by human standards. You need not rush outside to photograph it before breakfast. The timescales are measured in billions of years, but cosmologically the structure we observe now represents one stage in a changing universe. Earlier the web was less developed. Now it is strongly defined. In the far future, distant unbound regions will become increasingly isolated from one another. The web itself also raises an interesting question. How large can a structure become before it stops being useful to call it a structure? This becomes tricky because astronomers have identified enormous walls and concentrations extending across extraordinary distances. Some appear to stretch for more than 1 billion light years. But calling one of these arrangements a single object can be misleading. Imagine a chain of towns. Each town is connected to the next by suburbs and roads. If you keep connecting neighbouring built-up areas, you may eventually describe a region hundreds of kilometres long as one continuous settlement. That does not necessarily mean it behaves as one city. The same caution applies to giant cosmic structures. A very long chain of clusters and filaments can be connected statistically without being gravitationally bound as one object. At the larger scales, astronomers often care less about naming individual structures and more about measuring the overall distribution. This leads to one of the most important features of the universe. On very large scales, it becomes approximately homogeneous. That sounds strange after spending so much time discussing filaments, walls, clusters, and enormous empty voids. The key phrase is very large scales. If you examine a region a few million light years across, matter can be distributed extremely unevenly. You might land inside a dense galaxy cluster or in a void. Increase the region to hundreds of millions of light years, and the differences begin averaging out. Go larger still, and different sufficiently large volumes contain roughly similar average amounts of matter. The universe is not perfectly uniform, but beyond a certain scale it stops getting progressively lumpier. This property is an important part of modern cosmology. It means there is no evidence that our observable region sits inside some endlessly increasing hierarchy where every supercluster is inside a larger supercluster, which is inside something still larger forever. The structure has a characteristic transition. Below that scale, the cosmic web is obvious. Above it, the universe looks statistically smoother. That does not make the web smaller. Its filaments and walls remain absurdly large. It simply means they are features within an even larger distribution that becomes more uniform when averaged over enough space. This brings us to another term that is easy to misunderstand: the observable universe. The observable universe is the region from which light or other signals have had enough time to reach us since the early universe. It is not necessarily the entire universe. We do not currently know whether the full universe is finite or infinite. If it is finite, it may extend far beyond what we can observe. If it is infinite, then our observable region is only one finite portion of something much larger. The limit is created by the age and expansion history of the universe, not by a physical wall sitting at the edge. There is no giant boundary with darkness on one side and a sign saying, "End of universe. Please return during opening hours." When astronomers talk about structure across the observable universe, they mean structure within the region available to observation. The cosmic web almost certainly continues beyond our observable horizon if the larger universe resembles the region we can see, but we cannot simply look beyond that horizon. Light from sufficiently distant regions has not reached us, and because of accelerated expansion, some regions may never send signals that reach us in the future. This creates a peculiar situation. The universe can contain places that are physically part of the same overall cosmos, but permanently inaccessible to us, not merely far away, causally unreachable. No spacecraft could solve the problem by being patient enough. The expansion of space itself matters. For a species that has spent most of its history worrying about what lies over the next hill, this is a rather extreme version of inaccessible geography. Within the region we can study, though, astronomers have developed increasingly powerful ways to map the web. Large galaxy surveys measure millions of galaxies. Each one has a position on the sky. Its spectrum provides a redshift. From those measurements, astronomers estimate its distance and construct three-dimensional maps. The Sloan Digital Sky Survey was particularly influential in revealing the distribution of galaxies across huge volumes. Later surveys have expanded the number of measured objects and the volume mapped. When displayed in 3 dimensions, the resulting pattern can be striking. Dense arcs and strands appear. Clusters sit like knots. Voids open between them. The resemblance to a network is immediate. Other surveys map the web in different ways. Hydrogen gas can be traced through absorption lines. X-ray observations reveal extremely hot material. Radio observations detect gas and active galaxies. Gravitational lensing can map total mass. Future observations will make the dark matter distribution increasingly detailed without ever photographing dark matter directly. One technique known as weak gravitational lensing is especially powerful on large scales. Foreground matter slightly distorts the shapes of distant galaxies. The distortion of any individual galaxy is difficult to distinguish from its natural shape, but averaged together enormous numbers of background galaxies and a statistical pattern appears. That pattern reveals where mass lies along the line of sight. The result can be a map of matter independent of whether that matter emits light. In this way, astronomers can compare the locations of galaxies with the underlying mass field. Generally, galaxies follow the dark matter framework. Dense galaxy regions coincide with dense mass regions. But the relationship is not perfectly simple, because different types of galaxies form more efficiently in different environments. This introduces something cosmologists call galaxy bias. The word bias here does not mean that galaxies have developed unfair opinions about one another. It means galaxies do not necessarily trace matter with perfect proportionality. Some galaxy populations are more strongly clustered than others. Massive galaxies, for example, tend to inhabit more massive dark matter halos and denser environments. To reconstruct the matter distribution from galaxies, astronomers need to understand that relationship. This becomes important when the cosmic web is used to test cosmology. The pattern of large-scale structure contains information about the contents of the universe. More dark matter changes how quickly structures grow. Different properties of dark energy affect expansion and growth. The masses of neutrinos can influence structure formation, because fast-moving neutrinos do not cluster as easily on smaller scales. Even alternative theories of gravity can predict slightly different growth patterns. So a map of galaxies is also a test of fundamental physics. Every cluster position, every filament, every void, every statistical correlation between galaxies separated by hundreds of millions of light-years. All of it can contain information. One especially useful feature hidden in the galaxy distribution is known as baryon acoustic oscillations. In the early universe, ordinary matter and radiation supported pressure waves. These waves travelled through the hot plasma before the universe cooled enough for atoms to form and radiation to travel freely. They left behind a preferred scale in the later distribution of matter. Billions of years later, astronomers can detect a subtle statistical tendency for galaxies to be separated by this characteristic distance. It acts as a kind of standard ruler. By measuring how that scale appears at different times in cosmic history, researchers can study the expansion of the universe. This is a wonderful example of how the cosmic web preserves ancient information. The galaxies did not arrange themselves deliberately at a useful measuring distance. The pattern is a fossil of sound waves moving through the early universe. The modern structure remembers conditions from a time before any stars existed. Voids preserve information too. Because they are relatively empty, they respond differently to gravity and expansion than dense clusters do. Their shapes and growth can be sensitive to dark energy and theories of gravity. Researchers count voids, measure their sizes, examine galaxies around their edges, and compare the observations with simulations. The emptiness becomes data. Filaments can also affect galaxy evolution. Gas travelling through them can supply galaxies. Interactions in filaments are more common than in deep voids, but generally less extreme than in dense cluster cores. Galaxies may have their spins influenced by the direction in which matter arrives. Groups form along filaments before entering larger clusters. This means a galaxy's location within the web can affect its entire history. A galaxy in a void. A galaxy in a filament. A galaxy at a cluster node. They may begin with similar physical ingredients and end up with very different lives. The cosmic web is therefore more than a map showing where galaxies are. It is the environment in which galaxies develop, and if you continue moving down the hierarchy, the consequences eventually reach planets. A galaxy's environment affects its gas supply and merger history. That affects star formation. Star formation determines how many new planetary systems appear. Stellar generations change the abundance of heavy elements. Those elements become raw material for rocky planets. The largest patterns in the universe and the smallest environments we discussed earlier are not independent stories. They are linked by a chain of physical processes. A tiny rocky world can exist because earlier stars formed inside galaxies. Those galaxies grew inside dark matter halos. Those halos developed along the cosmic web. The web grew from density variations in the early universe. The structure around us is therefore connected across scale. That does not mean a filament directly controls whether it rains on Earth tomorrow. Weather forecasting remains safely local. But the material and environment that made Earth possible are part of a much larger history. Our cosmic address can now be read in both directions. Start here. Earth is a planet. It belongs to the solar system. The solar system is centered on the Sun. The Sun is one star among the enormous stellar population of the Milky Way. The Milky Way belongs to the local group. The local group sits within a broader region of galaxy flows and concentrations. Nearby clusters and groups trace larger structures. Those structures occupy filaments and walls separated by voids, and together, those features form the cosmic web across the observable universe. At each step, the previous structure becomes a small part of something larger. Earth feels enormous from the ground. From the Sun, it is a small planet. The solar system feels enormous until we compare it with the distances between stars. The Milky Way makes the solar system practically invisible. A map of galaxy clusters reduces the Milky Way to one point among billions. Then the cosmic web reduces entire clusters to knots. Scale has a way of being unsympathetic, but it also makes the universe easier to organise. Instead of thinking about an unimaginable number of separate objects, we can see a hierarchy shaped largely by gravity. Planets gather around stars. Stars can gather into clusters. Gas clouds produce new stars. Stars belong to galaxies. Galaxies gather into groups. Groups assemble into clusters. Clusters and groups lie along larger concentrations. Filaments, walls, and voids define the cosmic web. The details change at each scale, but gravity keeps appearing. It organises matter without needing a central planner, and there is no single point at the middle of all this structure. The cosmic web has no known central hub where everything originates. The expansion of the universe does not work like debris exploding outward from one point into pre-existing empty space. On sufficiently large scales, space itself expands. From any ordinary galaxy far from strong local gravitational complications, distant galaxies would generally appear to recede. There is no unique central galaxy, no privileged cluster, no obvious cosmic capital. The Milky Way is not at the centre. Neither is Andromeda, nor Virgo, nor Laniakea. Our location is simply one location inside the network. That can make the universe feel less arranged around us, but it also makes our ability to understand it more impressive. We occupy one planet around one star. From that small position, humans learn to measure distances to other stars, then galaxies, then clusters, then structures stretching across billions of light years. We discovered invisible matter by measuring gravity. We reconstructed the early universe from ancient radiation. We mapped structures too large for light to cross during the entire history of human civilization, and much of this was done by collecting photons that happened to arrive here after travelling across space for millions or billions of years. A telescope does not travel to the cosmic web. The web sends pieces of its history to us. Every distant galaxy is seen in the past. The farther away it is, the earlier we see it. So when large surveys map the universe, they are not creating a perfect snapshot of everything at one universal moment. They are looking down our past light cone. Nearby galaxies are seen relatively recently. Very distant galaxies are seen much earlier. The map includes time as well as distance. This allows astronomers to study how structure changed. Look nearby and the web is mature. Look farther back and galaxies become younger. Clusters become less developed. At sufficiently early times, the great modern network has not yet fully formed. The universe becomes smoother. Watching farther into space becomes a way of watching backward through cosmic construction. And there is still much we do not understand. We do not know what dark matter actually is. We know its gravitational effects extremely well, but its particle nature remains unknown. We do not know what dark energy fundamentally is. We can measure the accelerated expansion associated with it, but the underlying explanation remains one of the largest open questions in physics. We do not know exactly how the first stars and galaxies assembled in every detail. New observations continue finding surprisingly early galaxies and forcing astronomers to refine models of how rapidly structure developed. The cosmic web is well established. The full explanation of every ingredient inside it is not. That is often how science works. A broad picture becomes clear while individual pieces remain unresolved. We can map the skeleton before identifying every material from which it is built. We can describe how the web grows while still asking what most of its mass actually consists of. And perhaps that is an appropriate place to leave the scale of the universe for tonight. Not with everything answered, just with the map a little clearer. You began here on one small planet. Then the view widened to stars and planetary systems, crowded stellar clusters, giant molecular clouds, galaxies, galaxy groups, galaxy clusters, superclusters, filaments, walls, and voids. Now the separate pieces fit into one arrangement. The universe is not filled with galaxies scattered randomly through empty space. It has structure. Matter gathers. Gravity amplifies small differences. Dark matter provides much of the framework. Galaxies illuminate the densest regions. voids open between them. The whole pattern continues across the observable universe until, on still larger scales, those differences begin averaging into a more uniform cosmos. And somewhere inside one filament, inside one group, inside one spiral galaxy, around one fairly ordinary star, there is Earth. Perhaps the room around you is quiet now. Maybe the lights are low. Maybe you're still awake, which means the universe has once again turned out to be slightly more interesting than was strictly helpful for sleep. But there is no need to hold the entire cosmic web in your head. No one can picture billions of light years accurately in ordinary human terms. It is enough to know the arrangement. The stars above you are not isolated decorations. They belong to a galaxy. That galaxy has neighbours. Those neighbours belong to a much larger distribution, and the structure continues outward until individual galaxies disappear into an enormous network shaped over billions of years by gravity and expansion. If you found this slow journey through the structure of the universe soothing, interesting, or simply a pleasant way to spend some quiet time, you can give the video a like and subscribe to Science for Sleep. And if you're already beginning to drift off, there is nothing else you need to remember tonight. The galaxies will keep moving. Clusters will keep growing. Light will keep travelling through the darkness. Matter will continue following the structure laid out by gravity. And the cosmic web will remain out there on scales far beyond anything we can experience directly, while here, on one small world inside it, the night can become quiet again. Sleep well, fellow traveller, wherever in the web you happen to be.